Krispy Kreme donuts, Cheetos, and gummy bears are three of the world's most irresistible snacks. From golden rings of glazed perfection to crunchy cheese-dusted puffs to chewy bursts of fruity sweetness, each one is crafted through a precise blend of science and design. Today we go inside the factories to watch dough rise, corn transform, and gelatin mold into candy as we uncover how these legendary treats are made. Krispy Kreme's story began in 1937 in Winston-Salem, North Carolina, where Vernon Rudolph opened a small donut shop using a secret yeast-raised donut recipe he purchased from a New Orleans chef. He began by selling his hot donuts to local grocery stores, but the scent of freshly fried dough and sugar glaze drifting into the streets drew people to his bakery window. It wasn't long before the iconic "Hot Now" neon sign was born, symbolizing fresh, warm donuts just off the line. Since then, Krispy Kreme has grown into an international phenomenon, producing millions of donuts daily across their retail shops and large-scale manufacturing facilities known as donut factories or commissaries, supplying fresh product to satellite locations, grocery stores, and drive-thrus around the world. The journey of a Krispy Kreme donut begins with flour, specifically high-protein wheat flour chosen for its strength and ability to create the soft but resilient gluten structure needed for yeast-raised dough. This flour arrives in bulk, stored in large silos equipped with pneumatic conveying systems that deliver measured quantities directly into automated mixing tanks. Each batch of dough is a precise mixture of flour, water, sugar, yeast, non-fat milk solids, hydrogenated vegetable shortening, salt, and proprietary flavoring agents, the exact blend of which remains closely guarded. The dough mixing phase takes place in industrial planetary mixers capable of handling hundreds of kilograms at a time. The mixer first hydrates the flour and activates the yeast in warm water. As mixing begins, temperature, moisture, and mix speed are carefully monitored by programmable logic controllers. The dough must reach the optimal development window, soft and elastic, but not overmixed. This ensures that the final donuts rise uniformly and fry evenly. After about 8 to 12 minutes of intensive mixing, the dough is transferred to stainless steel troughs and conveyed via automated systems to the fermentation area. This first fermentation, or bulk proofing phase, takes place in temperature and humidity controlled chambers set to approximately 85 degrees Fahrenheit with 75% humidity. Over the next 30 to 45 minutes, yeast metabolizes the sugars in the dough, producing carbon dioxide and alcohol. This causes the dough to expand in volume while developing the light, airy texture that defines a Krispy Kreme donut. Sensors monitor the internal dough temperature and gas production, ensuring consistency across batches. When fermentation is complete, the dough is unloaded onto a sheeting line. The sheeting and cutting process is one of the most visually engaging parts of the production line. The dough is rolled out into a continuous sheet by heavy-duty rollers and calibrated to a consistent thickness, typically around 11 to 13 millimeters. The sheet moves onto a cutting belt where rotary die cutters stamp out the signature ring shape. These cutters operate at high speed, creating thousands of donut rings and holes per hour with perfect uniformity. Excess dough, called trim, is automatically collected, reworked, and reincorporated into the next batch to minimize waste. The cut donuts are transferred onto large proofing trays or mesh conveyor racks and sent into a second proofing chamber called the final proofer. This chamber is even more tightly controlled than the bulk fermentation room, maintaining a constant 95 degrees Fahrenheit and 85% humidity. Over 30 to 45 minutes, the donuts undergo final leavening, rising and forming their distinctive pillowy shape. The proofing stage is critical. Underproofed donuts will be dense and misshapen, while overproofed ones may collapse during frying. Dough height and gas content are continuously monitored using non-contact laser sensors and digital volume scanners. After the final proof, the trays automatically feed into the fryer, the heart of the Krispy Kreme process. The fryer is a massive, continuous flow oil bath filled with high-stability vegetable shortening, maintained at around 360 degrees Fahrenheit. Doughnuts are gently dropped into the oil by automated lifters. As they float, a timing chain system flips them once to ensure even cooking on both sides. Fry time is precisely controlled, usually about 60 to 90 seconds per side, allowing the exterior to develop a delicate golden crust while the interior remains light and fluffy. The frying process is closely monitored by thermal sensors and oil quality meters. Krispy Kreme has proprietary filtration and replenishment systems that keep the frying oil clean, free of burnt crumbs, and within a narrow window of oxidation levels. This not only ensures the clean taste and color of each donut, but also extends the usable life of the oil, a critical factor in cost and sustainability. Once the donuts exit the fryer, they rest briefly on a drip belt to allow excess oil to drain. Then they are conveyed directly toward the glazing waterfall, a mesmerizing curtain of warm, liquid sugar glaze that coats every donut as it passes beneath. The glaze is a simple but carefully balanced syrup of powdered sugar, water, and proprietary stabilizers. It is kept at a temperature of around 120 degrees Fahrenheit in recirculating stainless steel tanks. Pumps maintain a constant flow, and nozzles ensure even distribution across the entire conveyor width. As the glaze hits the hot donuts, it forms a thin, glossy shell that sets within seconds as the donuts cool. Cooling conveyors extend for several meters beyond the glazing station, allowing the donuts to gradually reach ambient temperature without forced cooling. A method that prevents condensation and preserves the smooth glazed surface. Airflow in this area is tightly controlled to minimize airborne contamination and ensure consistent texture. Once cooled, the donuts are ready for packaging or additional decoration. For original glazed donuts destined for stores or direct consumer sale, the journey ends here. But for filled or specialty varieties, another series of steps begins. Filled donuts are rerouted to the injection station, where precision nozzles insert a metered dose of custard, jelly, chocolate, or cream into each piece. Injection is performed at 2 or more points to ensure even distribution and avoid structural collapse. Cameras monitor each donut to verify fill weight and placement. Any underfilled units are automatically removed from the line. Donuts requiring additional toppings, such as sprinkles, icing, or chocolate drizzle, are routed through decorating lanes staffed by a combination of robotic arms and human decorators. Chocolate toppings are prepared in tempering tanks to maintain gloss and prevent bloom, while sprinkle and nut dispensers apply dry toppings using vibration-assisted feeding systems. Hand-finished premium varieties, such as holiday-themed or limited edition donuts, are often decorated by trained artisans in dedicated cleanroom-style stations to preserve product integrity and presentation quality. Once decorated or glazed, the donuts are transferred to the packaging line. Here, conveyors feed product into fill-seal machines that arrange the donuts into trays or boxes, apply protective covers, and label each package with the production date, batch code, and nutritional information. All packaging materials are food grade and pre-printed with Krispy Kreme branding. Weigh check stations confirm net weight compliance, while metal detectors scan for any foreign objects, a critical food safety measure mandated by global quality standards. Depending on the destination, donuts are either boxed for direct store delivery, loaded into display racks for retail locations, or packed into temperature-controlled shipping crates for wholesale distribution. Krispy Kreme employs a tightly synchronized distribution system often using just-in-time logistics models to ensure product freshness. Most donuts reach stores within hours of production, and many locations include hot glaze production lines so customers can enjoy fresh donuts straight off the line. In satellite locations without on-site frying, hot light donuts are delivered twice daily from centralized production facilities via insulated trucks, maintaining the iconic experience across locations. The journey of a Cheeto begins not with cheese, but with corn, specifically degermed cornmeal. This is the core base of every crunchy or puffed Cheeto. The corn used is typically a variety known as yellow dent corn, which is chosen for its high starch content, excellent expansion properties, and neutral flavor profile. This corn is milled in specialized facilities where the germ and bran are removed to create a shelf-stable, fine-grained meal. This meal is sifted to a precise particle size, usually around 300 to 600 microns, and then stored in sealed, climate-controlled silos at the plant. The cornmeal is fed into a large-scale extrusion system, the heart of the Cheetos process. The extruder is a sophisticated piece of equipment made up of a long, cylindrical barrel lined with rotating screws that apply both heat and mechanical shear. As cornmeal enters the extruder, water and steam are injected at controlled rates. The rotating screws knead and compress the mixture, raising the temperature and pressure to extreme levels, usually above 300 degrees Fahrenheit and up to 200 psi. The high moisture and heat gelatinize the starches in the corn, turning the meal into a dough-like mass. This transformation is fundamental. Gelatinization causes starch molecules to swell and burst, which is what enables expansion when pressure is suddenly released. At the end of the extruder is a die, a metal plate with precision-drilled holes that shape the product. As the hot, pressurized dough exits the die, it hits atmospheric pressure instantly. The sudden drop in pressure causes the water inside the dough to rapidly vaporize, making the dough puff out explosively. This is what gives Cheetos their airy, irregular shape. For the classic crunchy Cheetos, the die holes are small and circular, and the emerging dough is cut by a high-speed, rotating blade into finger-length segments. For puffed varieties, the die is different, designed to create a rounder, lighter texture, and the cutting speed is adjusted accordingly. From the extruder, these raw snacks, often called collets at this stage, are still pale and flavorless. They are immediately transferred via a vibratory conveyor into a high-temperature fryer or baking oven, depending on the product line. For traditional crunchy Cheetos, frying is the chosen method. The oil in the fryer is kept at approximately 350 to 375 degrees Fahrenheit, and the collets are cooked for around 45 to 60 seconds. During frying, any remaining internal moisture is driven off, and the starches harden into the crisp, glassy structure that gives Cheetos their famous crunch. Oil absorption is closely monitored and controlled, typically targeted between 18% and 25% by weight depending on the desired texture. In contrast, puffed Cheetos are usually baked in a high-capacity conveyor oven, where they are subjected to dry heat for several minutes. This method gives them a softer bite and lighter structure. Regardless of cooking method, the snacks are then passed through a cooling system, usually an ambient air tunnel or rotary drum, to bring them back to room temperature and stabilize their structure before seasoning. Next comes the most recognizable step of all: flavor coating. At this point, the collets are fully cooked and cooled, ready to receive their signature cheesy exterior. Flavoring is applied inside a rotating drum known in the industry as a tumble drum or seasoning barrel. As the Cheetos tumble inside, a fine mist of oil or binder is first sprayed onto their surface to help the seasoning powder adhere. Then the cheese powder is dispensed in precise amounts using auger-fed hoppers or pneumatic flavor delivery systems. The cheese powder blend used in Cheetos is a proprietary mixture that includes real cheddar cheese, which has been aged, dehydrated, and ground into a fine powder, as well as whey, buttermilk solids, monosodium glutamate, disodium phosphate, salt, and artificial or natural coloring agents like annatto and yellow hash 6. The powdered blend is engineered not only for flavor, but also for aroma, mouthfeel, and flowability. Anti-caking agents are included to prevent clumping, and fat content is carefully balanced to maximize adherence without greasiness. The coating process is not just a matter of dusting powder onto the snack. It requires extreme precision. Sensors in the tumble drum measure product throughput, and dosing equipment adjusts in real time to match the exact surface area being coated. Too much powder, and the product becomes clumpy and oily. Too little, and the iconic flavor is lost. The tumbling speed, drum angle, spray pressure, and dust feed rate are all variables that can be adjusted to ensure an even, flavorful coating on every single piece. Once coated, the finished Cheetos pass through a final quality control checkpoint. High-speed cameras and laser-based inspection systems examine the product for size, shape, and color. Defective pieces, those that are undercooked, broken, or improperly coated, are automatically removed from the line by pneumatic nozzles or rejection arms. Random samples are collected at regular intervals and sent to on-site labs, where technicians test for moisture content, oil content, seasoning distribution, and sensory quality. Some plants even perform audio analysis on the crunch sound of the product to ensure it meets the expected crispness profile. From here, the Cheetos head to packaging. Conveyor belts transport the product to vertical form-fill-seal machines, which form bags from rolls of printed film, fill them with a precise weight of product, and seal the bags using heat and pressure. Each bag is gas flushed with nitrogen to displace oxygen and preserve freshness, then printed with a date code, lot number, and batch information. The sealed bags move along a conveyor to robotic arms or gantry pickers, which group them into cartons or multi-packs, shrink wrap the boxes, and stack them onto pallets. These pallets are barcoded and transferred to climate-controlled storage areas or loaded directly onto distribution trucks. The entire operation is supported by advanced data tracking and control systems. Every ingredient lot, processing variable, and quality check is logged in real time. Supervisory control and data acquisition software allows operators to monitor temperature, pressure, and feed rates from centralized control rooms, adjusting parameters as needed. Predictive maintenance systems keep machinery running smoothly, while hygiene protocols ensure compliance with global food safety standards such as SQF, BRCGS, and HACCP. Cheetos production also has to account for allergen management. Since dairy is a major component of the cheese flavoring, all equipment that comes into contact with the powder must be sanitized during changeovers, and allergen segregation is built into plant design. From dedicated air handling systems to separate ingredient silos, employees are trained in food safety procedures and wear protective uniforms, including gloves, hairnets, and face shields to maintain cleanliness and prevent cross-contamination. While automation handles the bulk of production, human expertise still plays an important role. Line operators oversee machinery, quality technicians perform daily product evaluations, and sensory panels regularly sample batches to confirm that each variant, whether it's flamin' hot, white cheddar, or the classic crunchy, meets exact flavor and texture targets. In flavor development labs, food scientists experiment with new seasonings, test oil types, and run small batch trials to bring new innovations to market. The entire factory is designed not just for efficiency, but for sensory control. Cheetos are engineered to deliver maximum flavor in every bite, from the first crunch to the lingering umami finish. The orange color, for example, is formulated to trigger visual associations with cheesy richness. The texture is calibrated to shatter quickly and melt away, delivering a burst of salt, fat, and dairy-based flavor compounds to the tongue. This precise sensory engineering is backed by decades of research in flavor chemistry and consumer psychology, and it all starts with a humble puff of cornmeal. At the end of the day, producing a Cheeto is about more than just crunch. It's about delivering a consistent, craveable experience that millions of consumers around the world instantly recognize. Every puff that tumbles out of the seasoning drum carries the result of advanced thermodynamics, fluid mechanics, extrusion modeling, and food chemistry, executed at high speed in high volume with incredible consistency. From raw corn to crispy, cheese-dusted curl, the life of a Cheeto is a tour de force of modern snack food manufacturing. The history of gummy bears traces back to 1922, when Hans Riegel of Bonn, Germany, created the first dancing bear candy under the Haribo brand. His original version was softer and larger than today's standard gummy bear, but it set the template for what would become one of the world's most recognizable confections. Over time, the formula evolved, production was industrialized, and today's gummy bears, uniform in size, colorfully translucent, and resistant to melting, are produced in volumes of tens of thousands per hour in facilities that run 24/7. The core of every gummy bear is gelatin, a protein derived from collagen, typically sourced from pork or beef bones and skin. Gelatin provides the chewy, elastic texture that defines gummies. It arrives at the factory in powdered or sheet form and is stored in dry, airtight conditions until ready for use. To begin the process, the gelatin is rehydrated in large stainless steel mixing vessels by soaking it in purified warm water, allowing it to swell and dissolve into a thick, smooth solution. This step requires strict temperature control, usually between 130 degrees Fahrenheit and 150 degrees Fahrenheit, to fully activate the gelatin without breaking down its protein chains, which are essential for forming the final gel structure. Simultaneously, a sugar-glucose syrup blend is prepared. Cane sugar and liquid glucose are the primary sweeteners used, chosen for their flavor, crystallization behavior, and moisture-binding properties. Sugar gives sweetness and structure, while glucose syrup prevents crystallization and contributes to chewiness. The two ingredients are mixed and heated in a batch or continuous cooker to a temperature of around 230 degrees Fahrenheit to 240 degrees Fahrenheit. The resulting syrup is a thick, clear liquid that's highly viscous and extremely hot. This cooking step is tightly monitored. Undercooking leads to soft, unstable bears, while overcooking results in dense, rubbery textures. Once the sugar-glucose syrup reaches the target temperature, it is transferred to a vacuum chamber where moisture is rapidly removed under reduced pressure. This allows the syrup to cool slightly while achieving the proper water activity level. It is then blended with the gelatin solution and stirred gently to combine without introducing air bubbles. At this stage, acidulants such as citric acid or malic acid are added to balance the sweetness with a tart finish, depending on the flavor profile desired. With the base mixture ready, flavor and color are introduced. These ingredients are dosed with milliliter level accuracy, often by computer-controlled pumps and injectors. Natural and artificial flavorings, such as cherry, lemon, raspberry, pineapple, or apple, are used in carefully tested concentrations. Coloring agents may include natural sources like paprika, beet juice, or spirulina, or synthetic food colors such as red 40, yellow 5, or blue 1, depending on regional regulations and brand formulation. The final syrup mixture is now a hot, vividly colored liquid candy base, ready for depositing. But instead of being poured into metal molds, like hard candies, gummy bears are cast into starch molds. This is one of the most unique and visually interesting parts of the gummy production process. Starch molding, or the mogul process, is a method developed over a century ago and still used today due to its ability to handle high moisture gels without sticking. Cornstarch is loaded into large metal trays, several feet long and several inches deep. These trays pass under a stamping board fitted with rows of bear-shaped dies. As the dies press into the starch, they leave behind hundreds of identical impressions. Soft, dry cavities that will hold the gummy mixture. The starch serves several purposes. It absorbs excess moisture, supports the soft liquid form during gelling, and prevents sticking. The prepared candy mixture is pumped into these starch molds using multi-nozzle depositor heads. Each nozzle dispenses a precise dose of syrup into each cavity, accurate to within fractions of a gram. The depositor can alternate colors or blend them in the same cavity to produce two-toned or rainbow bears. Timing and flow rate are critical as the liquid begins to set almost immediately upon cooling. Once filled, the trays continue along the line and are stacked on racks inside a drying room. The drying or curing phase is critical to gummy bear texture and shelf life. Inside the drying room, maintained at about 68 degrees Fahrenheit and 20% relative humidity, the bears sit for 24 to 48 hours, slowly losing moisture and transforming from a thick syrup into a firm, bouncy gel. This moisture reduction changes the water activity of the product, giving it its chewy bite and protecting it against microbial spoilage. During drying, the bears shrink slightly, concentrate in flavor, and develop their familiar dense chewiness. Once dried, the trays are transferred to a demolding station where the bears are gently released from the starch molds. Specialized vibratory sieves and air jets remove excess cornstarch, which is collected, filtered, and reused in subsequent molding cycles. The gummy bears are now fully formed, but still require finishing touches before packaging. One important post-processing step is the application of a glazing agent. Without it, gummy bears can stick together in packaging or lose their visual appeal. The bears are tumbled in large rotating drums where they are sprayed or misted with a thin layer of carnauba wax, beeswax, or a vegetable oil-based glaze. This coating gives each bear a shiny finish, enhances mouthfeel, and provides a barrier against moisture exchange with the environment. Some formulations may also include anti-foaming agents or preservatives at this stage, depending on the desired shelf life and shipping conditions. Before packaging, the bears pass through a quality control and sorting line. Optical scanners and high-speed cameras inspect each piece for size, shape, and color accuracy. Misshapen or broken bears are rejected. Random samples are also collected for moisture content analysis, gel strength testing, and taste panels to ensure every batch matches the brand standards for flavor, bounce, and chew. Some facilities perform rheological tests using texture analyzers that press into the gummy and record resistance, measuring its elasticity and cohesiveness. Once passed, the finished gummy bears move to packaging lines. These high-speed systems funnel the bears into weighing hoppers, where load cells measure out exact quantities to the gram. The measured product drops into form-fill seal machines, which create bags from rolls of pre-printed plastic film, fill them, and seal them with heat. Date codes, batch numbers, and QR traceability codes are applied to each package, enabling full traceback in case of recalls or quality concerns. From here, the bags are grouped into display cartons, multi-packs, or larger bulk boxes using robotic arms and carton erectors. Final pallets are shrink-wrapped and scanned into the warehouse management system. Depending on destination and shelf life, the bears are either shipped immediately or held in climate-controlled storage to ensure freshness. Transport is conducted with care to avoid temperature extremes. High heat can cause gummies to fuse, while cold can compromise texture. Throughout the entire process, sanitation and food safety are paramount. Gummy bear facilities are regulated under international food safety certifications such as BRCGS or FSSC 22000. The journey begins with sourcing green coffee beans. Factories procure these beans in large quantities from coffee-growing regions such as Brazil, Colombia, Vietnam, and Ethiopia. Since instant coffee requires consistent flavor profiles, manufacturers often blend beans from various regions to create a balanced and standardized flavor. Upon arrival at the factory, the green coffee beans are subjected to rigorous quality control checks. Samples are tested for size, moisture content, and defects to ensure the beans meet the factory's standards for processing. Once approved, the beans are stored in massive silos made of food-grade stainless steel or aluminum to protect them from contamination, pests, and humidity. These silos are equipped with automated systems that precisely dispense beans onto the production line. The first major step in processing the beans is cleaning. Coffee beans, even after being cleaned at their origin, may still contain impurities such as dirt, stones, sticks, or metal fragments. In the factory, the cleaning process involves several stages. Vibrating screens sift the beans to remove large debris, while air classifiers blow away lighter materials like husks or dust. Magnets are used to extract any metallic particles. Some factories also employ optical sorting machines, which use cameras and sensors to identify and remove defective beans or foreign objects. This thorough cleaning ensures that only high-quality beans proceed to the roasting stage. Roasting is a critical step in developing the rich, complex flavors of coffee. Factories use industrial coffee roasters, which can process thousands of pounds of beans per hour. The roasting process is controlled by highly advanced systems that allow operators to customize the roast profile for specific flavor outcomes. For instant coffee, medium to dark roasts are commonly used, as they bring out bold flavors that translate well into the final soluble product. Roasting temperatures typically range between 370 and 540 degrees Fahrenheit, depending on the desired flavor profile. During roasting, the beans undergo the Maillard reaction, a chemical process that creates the characteristic aromas and flavors of coffee. The roasting equipment includes temperature sensors and real-time monitoring systems to ensure uniform roasting across large batches. Once the roasting is complete, the beans are cooled rapidly to stop the roasting process and prevent overcooking. Factories use air cooling systems or water spray cooling, depending on the setup. Cooling is an important step, as improperly cooled beans can lose their flavor or become brittle. After cooling, the beans are sent to grinding machines. The grinding stage reduces the roasted coffee beans into smaller particles, which will be used for the brewing process. Factories use industrial grinders, such as roller mills or hammer mills, capable of producing a consistent grind size. The grind size is crucial because it affects the extraction process that follows. For instant coffee, a relatively coarse grind is typically used to optimize the brewing process in the factory. The ground coffee is then stored in intermediate holding bins, where it is kept fresh until it is ready to be brewed. Brewing is the next major step in instant coffee production, and it is carried out on an industrial scale. Massive brewing systems, similar to oversized percolators, are used to extract the soluble compounds from the ground coffee. These systems consist of large stainless steel extraction tanks or columns, which are designed to hold thousands of gallons of water and coffee grounds. Hot water is circulated through the coffee grounds at precise temperatures and pressures, mimicking the brewing process used at home, but on a much larger scale. Typically, water temperatures range between 190 and 205 degrees Fahrenheit, and the brewing time is carefully controlled to maximize flavor extraction while minimizing bitterness. The brewed coffee concentrate, a liquid containing the extracted soluble compounds, is then filtered to remove the spent coffee grounds. Factories use advanced filtration systems, such as centrifugal separators or fine mesh filters, to ensure that no solid particles remain in the liquid. The spent grounds are often dried and repurposed as fertilizer or biomass fuel, making use of every part of the raw material. At this stage, the coffee concentrate is a highly aromatic liquid, but it is still far from the final product. The challenge is to transform this liquid concentrate into a stable, dry, and soluble form. Factories use one of two main methods for this: spray drying or freeze drying. Spray drying is a fast and cost-effective method that is commonly used to produce instant coffee powder. The coffee concentrate is first preheated to reduce its moisture content. It is then pumped into a tall, spray drying chamber equipped with nozzles that disperse the liquid into fine droplets. At the same time, hot air, typically around 480 degrees Fahrenheit, is blown into the chamber. As the droplets fall through the chamber, the water in the coffee concentrate rapidly evaporates, leaving behind fine coffee powder. Spray drying is efficient and capable of processing large volumes, but the high temperatures can sometimes lead to a slight loss of flavor and aroma. Freeze drying, on the other hand, is a more delicate and sophisticated process that better preserves the natural flavors and aromas of coffee. The coffee concentrate is first frozen at extremely low temperatures, usually around 40 degrees Fahrenheit, to form solid slabs or granules. These frozen coffee pieces are then placed in a vacuum chamber. Inside the chamber, the frozen water in the coffee undergoes sublimation, a process where ice turns directly into vapor without passing through the liquid phase. This method requires precise control of temperature and pressure and takes longer than spray drying, but it produces high-quality granules of instant coffee that dissolve easily in water. After the drying process, the instant coffee is sifted and graded by particle size to ensure uniformity. Any oversized or undersized particles are removed, and the coffee is blended to create a consistent final product. Factories conduct rigorous quality control tests at this stage, including flavor analysis, solubility testing, and moisture content measurement. These tests ensure that the instant coffee meets the desired standards for flavor, aroma, and texture. Packaging is the final step in the production process, and it is designed to protect the coffee from moisture and preserve its freshness. The dried instant coffee is transported to high-speed filling machines, which dispense precise amounts of coffee into jars, tins, or pouches. Factories use nitrogen flushing systems to replace oxygen in the packaging, as oxygen can degrade the coffee over time. The jars are sealed with airtight lids, while pouches are heat sealed to maintain freshness. After sealing, the packages move to labeling stations, where automated systems apply branding, ingredient lists, and expiration dates. Each package undergoes a final inspection using vision systems to ensure there are no defects in the seals or labels. Once approved, the packages are packed into cartons or cases using robotic packing systems and prepared for shipping. Pallets of instant coffee are stacked and wrapped for stability before being loaded onto trucks or containers for global distribution. Throughout the entire process, factories rely on advanced automation and engineering to ensure efficiency and consistency. Programmable logic controllers and supervisory control and data acquisition systems monitor and control every stage of production, from roasting and brewing to drying and packaging. Real-time data on temperature, pressure, humidity, and other parameters allows operators to make precise adjustments as needed, minimizing waste and ensuring high-quality output. Hygiene and food safety are also paramount in instant coffee production. Production areas are designed with food-grade stainless steel surfaces, seamless flooring, and clean room environments to prevent contamination. Positive air pressure systems are used to keep airborne particles out of critical areas, and employees are required to follow strict hygiene protocols. including wearing protective clothing and adhering to cleaning schedules. Factories are regularly inspected and certified to meet international food safety standards. Inside a tea factory, the transformation of fresh tea leaves into the familiar tea bags, loose leaf tea, or powdered varieties is a carefully orchestrated process. It is a seamless blend of tradition, precision engineering, and science. Every step of the way, from leaf intake to packaging, is designed to preserve the flavor, aroma, and quality that tea enthusiasts have come to expect. While the type of tea being produced, whether black, green, oolong, or white, dictates specific steps in the process, the overall journey is one of meticulous attention to detail, where both manual expertise and advanced machinery play vital roles. The process begins at the tea gardens, where leaves from the Camellia sinensis plant are plucked at peak quality. For most teas, workers handpick only the top 2 leaves and a bud from each branch, as these tender parts of the plant produce the best flavor and aroma. After harvesting, the leaves are transported to the factory as quickly as possible to prevent spoilage or fermentation during transit. Many tea factories are strategically located near plantations to minimize delays and ensure freshness. Upon arrival at the factory, the tea leaves are weighed and inspected for quality. Modern tea factories are equipped with automated intake systems that separate leaves from debris such as twigs or foreign matter. Vibrating conveyor belts or mechanical sieves are commonly used at this stage to remove unwanted materials. For higher grade teas, additional manual inspections may be carried out to ensure only the finest leaves proceed to the next step. The fresh leaves are then carefully spread out in thin layers on large trays or conveyor belts, marking the beginning of the first stage in tea processing. Withering. Withering is a critical step in tea production, as it reduces the moisture content of the fresh tea leaves and prepares them for the subsequent stages of processing. In the factory, withering is typically carried out in withering troughs, long, shallow trays equipped with a system of fans and controlled airflow. Fresh tea leaves are laid out on these trays, and air is circulated over them for several hours to slowly remove moisture. For black tea, withering may last anywhere from 12 to 18 hours, while green tea requires a shorter withering time, as it needs to retain more of its fresh, grassy flavor. Temperature and humidity are carefully controlled using automated climate systems to ensure consistent results. During this stage, the leaves become softer and more pliable, making them ready for rolling. The next stage is rolling, where the tea leaves are twisted and shaped to release their essential oils and initiate oxidation if required, as with black and oolong teas. Factories use large mechanical rolling machines equipped with heavy, grooved plates or rollers. These machines apply pressure to the leaves, breaking down their cell walls and releasing their natural juices. The released juices react with oxygen in the air, beginning the oxidation process that gives black tea its characteristic flavor and color. Rolling machines can be adjusted to produce different shapes and textures, depending on the type of tea being made. For example, green teas may be rolled into tight pellets for varieties like gunpowder tea, while black teas are often left in long, wiry shapes. At this point, the production process diverges depending on the type of tea being manufactured. For black tea, oxidation is the next key step. Oxidation, often mistakenly referred to as fermentation, is a chemical process that darkens the tea leaves and develops the rich, robust flavors associated with black tea. In factories, oxidation typically takes place in large, temperature-controlled rooms, where rolled tea leaves are spread out on trays or conveyor belts. These rooms maintain a controlled environment with high humidity and a temperature of around 77 to 86 degrees Fahrenheit. The leaves are periodically monitored to ensure they achieve the desired level of oxidation, which can take anywhere from 30 minutes to several hours, depending on the tea. As the leaves oxidize, they turn from green to a reddish-brown color, releasing the aromatic compounds that define black tea. In contrast, for green tea production, oxidation is intentionally prevented. To preserve the vibrant green color and fresh vegetal flavor of the leaves, factories employ a process called fixation, also known as kill green. This step involves heating the leaves immediately after rolling to deactivate the enzymes that cause oxidation. Factories use either steam or dry heat for this purpose. For Japanese-style green teas, like sencha, the leaves are steamed in specialized machines, while Chinese-style green teas are often pan-fried in large heated woks or rotating drum roasters. Fixation requires precise temperature control, as overheating can burn the leaves and underheating can fail to stop oxidation completely. Once oxidation or fixation is complete, the next step is drying, which reduces the moisture content of the tea to make it shelf stable. Drying is typically carried out in large industrial dryers or ovens equipped with temperature controls and airflow systems. Conveyor belt dryers, in which the leaves are gradually moved through a heated chamber, are common in large-scale tea factories. The temperature during drying ranges from 194 to 248 degrees Fahrenheit, depending on the type of tea and the desired final moisture content, which is usually around 3 to 5%. This step is crucial for locking in the flavor and aroma of the tea while ensuring it will not spoil during storage. After drying, the tea leaves are sorted and graded. In the sorting process, leaves are separated by size, shape, and quality using a combination of vibrating sieves, air separators, and optical sorting machines. Whole leaves, broken leaves, and small particles are separated into different grades, which are used for various tea products. For instance, whole leaves are often reserved for premium loose-leaf teas, while smaller particles are used for tea bags. Some factories also employ advanced laser sorting machines that can detect and remove any remaining foreign objects or off-spec leaves. Blending is another key step in tea production, especially for brands that aim to create consistent flavor profiles. Many teas are blended by mixing leaves from different regions, harvests, or even types of tea. Blending is carried out in large rotating drums or mixing machines, where precise quantities of different teas are combined to achieve the desired flavor. For flavored teas, additional ingredients such as dried fruit pieces, herbs, or essential oils are added during this stage. For example, Earl Grey tea is made by blending black tea leaves with bergamot oil, while chai blends often include spices like cinnamon, cardamom, and cloves. Once the tea has been blended and sorted, it is ready for packaging. Packaging is a highly automated process in modern tea factories. For loose-leaf tea, the leaves are weighed and sealed in airtight bags, tins, or foil-lined pouches to preserve freshness. For tea bags, the leaves are measured and packed into filter paper, which is then cut and sealed into individual tea bags using high-speed machines. Many factories also produce pyramid-shaped tea bags, which allow for larger leaves and better infusion. After filling, the tea bags are placed into cartons or boxes, which are sealed and labeled with branding, lot numbers, and expiration dates. Throughout the entire process, quality control plays a vital role in ensuring the tea meets rigorous standards. Factories employ trained tea tasters who sample the tea at various stages of production to assess its flavor, aroma, and appearance. Advanced laboratory equipment is also used to measure moisture content, microbial activity, and other parameters that affect the quality and safety of the final product. Additionally, factories must comply with food safety regulations and certifications, such as ISO 22000 or HACCP, to ensure their tea is safe for consumption. Cocoa powder, the cornerstone of countless recipes from rich chocolate cakes to creamy hot cocoa, is the product of a complex and fascinating manufacturing process that combines agricultural expertise with advanced industrial engineering. Behind every tin or packet of cocoa powder lies a detailed, multi-step operation where raw cacao beans are transformed into the fine, flavorful powder that has become a staple ingredient in kitchens around the world. This process begins on cacao farms and culminates in a factory where specialized equipment and precise techniques ensure the consistency, flavor, and quality of the finished product. Let's take an in-depth journey into how cocoa powder is made, exploring each stage of the process, from bean to powder. The story of cocoa powder begins with the cacao tree, which thrives in tropical regions near the equator, such as West Africa, Southeast Asia, and Central and South America. The cacao tree produces pods that contain cacao beans surrounded by a sweet, sticky pulp. These beans are the raw material for cocoa powder. Once harvested, the pods are split open to extract the beans, which are then immediately subjected to the first critical step in the process: fermentation. Fermentation is a natural and essential process that develops the flavor precursors in cacao beans. After being removed from the pods, the beans and their surrounding pulp are placed into shallow wooden boxes or large banana leaf-lined baskets, where they ferment over a period of 5 to 7 days. During this time, natural yeasts and bacteria break down the sugars in the pulp, generating heat and causing the temperature in the fermentation pile to rise significantly, often reaching over 120 degrees Fahrenheit. This heat triggers a series of chemical reactions within the beans, developing their characteristic chocolate flavor while reducing bitterness. The beans are turned periodically to ensure even fermentation and prevent spoilage. Once fermentation is complete, the beans are removed from the boxes or baskets and sent to the next stage: drying. Drying is critical for stabilizing the fermented beans and reducing their moisture content to a level suitable for storage and transport. Traditionally, cacao beans are dried under the sun, spread out in thin layers on large drying racks or patios, and turned regularly with wooden rakes to ensure even drying. In modern cocoa production, factories may use mechanical dryers when weather conditions are unsuitable for sun drying or to speed up the process. These machines blow heated air over the beans to achieve the target moisture content, which is usually around 6 to 7%. Proper drying is essential because any excess moisture could lead to mold growth during storage or shipping. Once dried, the beans are sorted, graded, and packed into jute bags or bulk containers, ready for shipment to processing facilities. Upon arriving at the cocoa processing factory, the dried cacao beans are carefully inspected for quality. Factories use advanced optical sorting machines equipped with cameras and lasers to identify and remove defective beans, such as those that are cracked, moldy, or undersized. Any remaining debris, like stones or twigs, is removed using vibrating screens and air separators. Once the beans are cleaned, they are stored in large silos made of food-grade stainless steel, which protects them from contamination while allowing for easy access as the beans move through the production line. The first step inside the factory is roasting, a critical stage that brings out the rich chocolatey aroma and flavor of the beans. Industrial roasters are designed to handle large volumes of cacao beans, roasting them at precise temperatures that can range from 250 to 300 degrees Fahrenheit. The exact temperature and duration of roasting depend on the type of cocoa powder being produced, as darker roasts develop more intense flavors, while lighter roasts preserve subtle fruity or floral notes. During roasting, the shells of the beans become brittle, and the internal nibs, which contain the cocoa solids and cocoa butter, begin to separate from the shell. Sensors and computer-controlled systems monitor the roasting process to ensure consistency across batches. Once roasting is complete, the beans are rapidly cooled, using air or water to prevent overcooking. The next stage is winnowing, where the roasted beans are cracked open to separate the nibs from the outer shells. This process is carried out using winnowing machines, which use a combination of mechanical rollers and air currents to break the shells and blow them away. The result is a pile of clean, roasted nibs, which are the purest form of cacao and the raw material for all cocoa products. The nibs are then ground into a thick, viscous liquid known as cocoa liquor, despite containing no alcohol. The grinding process involves heavy-duty industrial grinders, such as roller mills or stone grinders, which crush the nibs into tiny particles. This process releases the natural cocoa butter within the nibs, creating a smooth liquid that flows easily. The particle size is reduced to less than 30 microns during this stage to ensure a silky texture. Cocoa liquor is the base ingredient for many chocolate products, but for cocoa powder production, the focus shifts to separating the two main components of the liquor, cocoa solids and cocoa butter. The separation of cocoa solids and cocoa butter is achieved through pressing. Cocoa liquor is fed into hydraulic or screw presses, which apply immense pressure, up to 6,000 pounds per square inch, to squeeze out the cocoa butter. This process leaves behind a solid cake of compressed cocoa solids. The extracted cocoa butter is collected and filtered for use in other products, such as chocolate bars, cosmetics, or pharmaceuticals. Meanwhile, the cocoa cake, which still contains a small amount of residual fat, becomes the foundation for cocoa powder. The cocoa cake is cooled and broken into smaller chunks before being fed into pulverizing machines, where it is ground into a fine powder. Factories use various types of grinding equipment, such as pin mills or ball mills, to achieve the desired particle size for cocoa powder. This step is critical for ensuring that the final product has a consistent texture and dissolves easily in liquids. The fineness of cocoa powder can vary depending on its intended use. For example, baking-grade cocoa powder is typically ground finer than drinking cocoa. At this point, the cocoa powder is almost ready, but one additional process may take place depending on the type of cocoa being produced: alkalization, also known as Dutch processing. Alkalization involves treating the cocoa powder with an alkaline solution, such as potassium carbonate. This process neutralizes the natural acidity of the cocoa, darkens its color, and gives it a smoother, milder flavor. Alkalized cocoa powder is often used in baking and beverages, as its reduced acidity reacts differently with leavening agents like baking soda. Once the cocoa powder is fully processed, it undergoes rigorous quality control tests to ensure it meets the manufacturer's standards. Samples are tested for flavor, color, pH levels, fat content, and particle size. Factories use advanced laboratory equipment, such as spectrophotometers and viscometers, to measure these properties with precision. Any deviations from the desired specifications are identified and corrected before the product moves to the packaging stage. Packaging is the final step in the production process, and it plays a critical role in preserving the freshness and quality of the cocoa powder. The powder is first sifted to remove any clumps or oversized particles, ensuring a uniform texture. It is then transferred to automated filling machines, which dispense precise amounts of cocoa powder into containers, such as tins, pouches, or bulk bags. For retail packaging, the containers are often flushed with nitrogen gas before sealing to remove oxygen and prevent spoilage. Labels are applied to the packages, including information such as the brand, product type, lot number, and expiration date. Once packaged, the cocoa powder undergoes a final round of inspections, where advanced vision systems check for defects such as improper sealing, misaligned labels, or damaged containers. The finished products are then packed into cartons or cases using robotic packaging systems. Palletizing robots stack the cartons neatly onto pallets, which are shrink-wrapped for stability and loaded onto trucks or shipping containers for distribution. The process begins with the careful selection and sourcing of raw ingredients. The primary components of KitKat bars include wheat flour, sugar, cocoa mass, cocoa butter, milk powder, vegetable oils, and emulsifiers. Nestlé, the brand behind KitKat, sources these ingredients from various regions worldwide, ensuring sustainability and adherence to strict quality standards. The cocoa used in KitKat is primarily sourced from the Nestlé Cocoa Plan, which promotes sustainable farming practices and fair trade. Once the raw materials arrive at the production facility, they undergo a series of inspections and tests to verify purity, consistency, and compliance with food safety regulations. This includes spectroscopic analysis for contaminants, moisture content testing, and sensory evaluations conducted by trained professionals. Once approved, the ingredients are stored in temperature-controlled silos and dispensing systems. The flour is kept in airtight storage to prevent contamination, while cocoa and milk powder are maintained under controlled humidity conditions to prevent clumping. Automated feeding systems transport these raw materials to the respective processing units, ensuring precise measurement and consistency in formulation. The first major step in KitKat production is wafer baking. The signature light and crispy wafer layers are created through a precise blending of wheat flour, water, sugar, and vegetable oils. Large industrial mixers, equipped with programmable logic controllers, ensure thorough mixing to produce a smooth and homogeneous batter. Once mixed, the batter is transferred via pressurized pumps to high-speed continuous wafer baking ovens. These ovens feature rotating baking plates that evenly distribute the batter across the surface, forming thin sheets of wafer. The baking plates operate at carefully controlled temperatures, typically around 180 to 200 degrees Celsius, ensuring uniform texture and color. The baked wafer sheets emerge golden brown and crisp, ready for the next stage. To enhance the crispness, the wafer sheets pass through a controlled cooling system. Conveyor belts transport the freshly baked wafers through a cooling tunnel, where calibrated fans gradually reduce the temperature to prevent thermal shock. The cooled wafers are then directed to the trimming and cutting station. Automated guillotine cutters trim the edges of the wafers to achieve uniform dimensions, ensuring consistency across all KitKat bars. Once trimmed, the wafers are transported to the layering station. Here, a fine layer of chocolate cream filling made from a precise blend of cocoa, sugar, and milk powder is evenly spread onto the wafers. Automated depositor machines ensure the filling is applied uniformly, maintaining the right thickness for optimal texture. The layering process continues with additional wafer sheets stacked on top, creating a multi-layered wafer slab. These slabs are then pressed under controlled pressure to bond the layers together without crushing the delicate structure. After layering, the wafer slabs proceed to the cutting stage. High-speed rotary or ultrasonic blade systems slice the large wafer sheets into precise rectangular portions, forming the individual KitKat fingers. Ultrasonic cutting technology is particularly effective in ensuring clean, precise cuts without generating excess crumbs or damaging the layers. The next crucial step is chocolate enrobing. The enrobing process begins with the preparation of molten milk chocolate, which is produced in large conching machines. These machines continuously grind and blend cocoa mass, cocoa butter, sugar, and milk powder, refining the mixture to achieve a smooth, velvety consistency. The conching process, which can last several hours, helps develop the rich, creamy texture and enhances the flavor profile of the chocolate. Once ready, the molten chocolate is fed into enrobing machines, where KitKat fingers pass through a curtain-like flow of chocolate. These enrobers ensure complete coverage, with excess chocolate removed using controlled air jets and vibrating conveyors. To achieve the signature glossy finish, the enrobed bars pass through a tempering unit, which carefully regulates the chocolate's crystallization process. This involves a precise cycle of heating, cooling, and reheating to stabilize the cocoa butter crystals, preventing bloom and ensuring a smooth, even texture. Following enrobing, the chocolate-covered KitKat bars enter a cooling tunnel. This tunnel, equipped with multi-zoned cooling technology, gradually reduces the temperature in stages to solidify the chocolate coating without causing cracks or condensation. The cooling process is carefully monitored using infrared sensors to maintain consistency. Once the chocolate is fully set, the KitKat bars move to the quality control and inspection stations. Advanced vision inspection systems, equipped with high-resolution cameras, scan each bar for defects, such as uneven coating, improper sizing, or misaligned layers. Bars that do not meet quality standards are automatically rejected by robotic sorting arms and sent for reprocessing. Additional quality checks include weight verification, moisture content analysis, and sensory testing conducted by trained specialists. After passing inspection, the KitKat bars are transported to high-speed wrapping machines. Individual bars are wrapped in foil or plastic film using heat sealing technology, ensuring airtight packaging that preserves freshness. These wrapped bars are then grouped into multi-packs, which are subsequently boxed using robotic case packers. The packaging design is carefully printed with product details, barcodes, and branding elements before final sealing. The packaged KitKat bars are then palletized for distribution. Automated palletizing systems stack the boxes onto pallets in a precise arrangement to optimize space utilization during transportation. These pallets are shrink-wrapped for stability and loaded onto temperature-controlled trucks for delivery to distribution centers worldwide. The logistics process is carefully coordinated to ensure timely delivery, with real-time tracking systems monitoring shipments from factory to retailer. Throughout the entire production process, extensive quality control measures are in place to uphold product integrity. Each batch undergoes rigorous laboratory testing, including microbiological screening, allergen testing, and texture analysis. Data from all processing stages is logged in automated tracking systems, allowing full traceability and compliance with food safety regulations. While the fundamental principles of KitKat production remain consistent across different manufacturing plants, regional variations may exist to cater to local tastes and preferences. For example, KitKat flavors such as matcha green tea, strawberry, and sake are produced in Japan using specialized formulations. Some factories may also incorporate alternative chocolate blends, varying cocoa content to suit market demands. Nestlé continues to innovate and optimize KitKat production through advancements in automation, sustainability initiatives, and ingredient sourcing. Modern factories are increasingly utilizing AI-driven quality control systems, energy-efficient processing equipment, and eco-friendly packaging solutions to reduce environmental impact. With continuous improvements in manufacturing technology, KitKat remains a global favorite, offering consumers a consistently delightful chocolate experience in every bite. Mars bars, one of the most iconic chocolate confections in the world, are produced in highly sophisticated manufacturing facilities designed to ensure consistency, efficiency, and quality at every step of the process. The production of Mars bars involves multiple intricate stages, from sourcing and processing raw ingredients to forming, enrobing, cooling, and packaging the final product. Each step is meticulously controlled using advanced automation technology and stringent quality control measures to ensure the signature caramel, nougat, and chocolate combination is perfectly replicated in every bar. The process begins with the careful selection of raw ingredients. The main components of a Mars bar include sugar, cocoa mass, cocoa butter, skimmed milk powder, whey powder, palm fat, glucose syrup, lactose, milk fat, and egg whites. These ingredients are sourced from trusted suppliers and undergo rigorous quality assurance checks upon arrival at the factory. Sugar, which plays a crucial role in both the nougat and caramel layers, is stored in large silos, where it is kept dry and free from contamination. Cocoa products, including cocoa mass and cocoa butter, are stored in climate-controlled environments to prevent degradation. Dairy ingredients, such as skimmed milk powder and whey powder, are tested for purity and consistency before use. Once the raw ingredients are approved, the first major stage in Mars bar production is the creation of the nougat layer. Nougat is a key structural component of the bar, providing a soft, chewy texture that contrasts with the caramel and chocolate. The nougat making process begins in large industrial mixing tanks, where a combination of sugar, glucose syrup, and water is heated to create a syrup. This syrup is then aerated using a whipping system, which incorporates fine air bubbles to achieve the desired light and fluffy texture. During this stage, egg whites or hydrolyzed soy protein are added as stabilizers to maintain the nougat's consistency. Once the nougat mixture reaches the proper texture, it is transferred onto a continuous conveyor belt, where it is spread into an even layer. This belt passes through a cooling tunnel to allow the nougat to set before it reaches the next stage of the process. The cooled nougat layer is then precisely cut into rectangular strips using high-speed guillotine cutters. These strips will form the base of each Mars bar. The next step in the process is the caramel layer. The caramel used in Mars bars is created through a controlled cooking process that involves heating sugar, glucose syrup, and milk ingredients to high temperatures. This process requires careful monitoring to achieve the perfect balance of sweetness and viscosity. Industrial batch cookers equipped with automated temperature controls ensure that the caramel reaches the ideal consistency before it is deposited onto the nougat base. The caramel is applied as a continuous sheet over the nougat layer, ensuring even distribution and uniform thickness. Once the caramel is applied, the combined nougat and caramel layers proceed through a controlled cooling tunnel, where the temperature is gradually reduced to allow the caramel to set without becoming too hard or sticky. This ensures that the layers remain cohesive and easy to cut in the next stage of production. After cooling, the layered nougat and caramel sheets are fed into an automated cutting system, which uses precision blades to slice them into individual bar-sized portions. These freshly cut bars are then transported via conveyor belts to the enrobing station, where they receive their final chocolate coating. The enrobing process is a critical step in Mars bar production, as it gives the bars their signature smooth milk chocolate exterior. The chocolate coating is made from a blend of cocoa mass, cocoa butter, sugar, and milk powder, which is carefully tempered to achieve the perfect texture and glossy finish. The tempering process involves heating and cooling the chocolate in a controlled manner to ensure the cocoa butter crystals form a stable structure, preventing fat bloom and ensuring a smooth mouthfeel. At the enrobing station, the cut nougat and caramel bars pass through a curtain-like waterfall of molten chocolate, which fully coats them. Excess chocolate is removed using controlled air jets and vibrating conveyors to ensure an even layer without excessive buildup. Some factories use a two-stage enrobing process, where an initial thin layer of chocolate is applied as a base coat before the final, thicker chocolate layer is added. After enrobing, the chocolate-covered bars enter a multi-zone cooling tunnel, which gradually reduces their temperature in controlled stages. This cooling process allows the chocolate to set properly without developing cracks or a dull surface. The bars emerge from the cooling tunnel with a perfectly set chocolate shell, ready for the final stages of quality control and packaging. Quality control is a fundamental part of Mars bar production, ensuring that only bars meeting strict standards reach consumers. Automated vision inspection systems equipped with high-resolution cameras scan each bar for defects such as uneven coating, misshapen forms, or inconsistencies in size. Bars that do not meet the required specifications are automatically rejected and sent for reprocessing. Additional quality control measures include weight checks using precision weighing systems, texture analysis, and sensory evaluations conducted by trained specialists. Once the bars pass quality inspection, they proceed to the packaging area, where high-speed wrapping machines individually wrap each bar in foil or plastic film. These machines use heat sealing technology to create airtight packaging that preserves freshness and prevents contamination. The wrapped bars are then grouped into multi-packs and placed into branded cartons, which are sealed and labeled using automated case packing systems. The final step in the process is palletization and distribution. Automated palletizing systems stack the packaged bars onto pallets in a precise arrangement to optimize space utilization during transportation. The pallets are shrink-wrapped for stability and loaded onto temperature-controlled trucks for distribution to retail stores and supermarkets worldwide. The entire logistics process is carefully coordinated to ensure timely delivery while maintaining the product's freshness and quality. Throughout the entire manufacturing process, Mars maintains stringent quality control and food safety standards. Each production batch undergoes extensive laboratory testing, including microbial analysis, allergen testing, and moisture content verification. The company also invests in sustainable sourcing initiatives, ensuring that key ingredients such as cocoa and palm oil are responsibly sourced to minimize environmental impact. Different Mars manufacturing facilities may incorporate slight variations in processing techniques based on regional ingredient availability, consumer preferences, or proprietary formulations. Some facilities may use alternative chocolate blends with varying cocoa content to cater to specific markets, while others may modify the nougat formulation for textural differences. Additionally, Mars continuously invests in research and development to improve efficiency, reduce energy consumption, and enhance sustainability in its production processes. With advancements in automation, AI-driven quality control systems, and eco-friendly packaging innovations, the production of Mars bars continues to evolve while maintaining the signature taste and texture that consumers have loved for generations. Twix, one of the world's most beloved chocolate bars, is manufactured using a highly sophisticated and automated process that ensures each bar maintains its signature combination of crunchy biscuit, smooth caramel, and creamy milk chocolate coating. The production of Twix bars occurs in state-of-the-art factories that utilize precision engineering, cutting-edge food processing technology, and rigorous quality control protocols. From the sourcing of raw ingredients to packaging and distribution, every step is carefully orchestrated to guarantee consistency, efficiency, and superior taste. The process begins with the selection and procurement of high-quality raw materials. The key ingredients in Twix bars include wheat flour, sugar, palm oil, cocoa butter, skimmed milk powder, cocoa mass, lactose, whey powder, salt, and emulsifiers. These ingredients are sourced from carefully vetted suppliers who must meet strict food safety and sustainability requirements. For instance, the cocoa used in Twix bars is sourced through Mars' Cocoa for Generations initiative, ensuring ethical sourcing and environmental responsibility. Similarly, the palm oil used in the biscuits and caramel is certified sustainable to reduce environmental impact. Upon arrival at the manufacturing facility, the raw ingredients undergo thorough quality checks before entering the production process. These checks include spectroscopic analysis to detect contaminants, moisture content analysis to ensure freshness, and sensory evaluations to verify taste and aroma. Ingredients that meet the necessary standards are then stored in temperature-controlled silos and storage units to maintain their quality. The first step in the actual production process is the creation of the biscuit base. Twix bars are distinguished by their crunchy, shortbread-like biscuit layer, which requires precise preparation and baking. The process begins in large industrial mixers, where wheat flour, sugar, palm oil, and leavening agents are combined to form a dough. The mixing process is carefully timed to ensure the dough reaches the ideal consistency, firm enough to hold its shape during baking, yet tender enough to create the signature crisp texture. Once the dough is fully mixed, it is transferred to an automated sheeting system. This system rolls the dough into a uniform sheet of the exact thickness required for Twix bars. The sheeted dough then moves to a rotary cutting machine, which stamps out individual biscuit fingers. Each biscuit is precisely cut to ensure uniform size and shape, allowing for seamless assembly in later stages. The cut dough pieces are placed onto conveyor belts and transported into a large industrial baking oven. These ovens operate using a continuous baking system where the biscuit fingers travel through different heat zones that gradually bake them to perfection. The baking temperature is carefully controlled, typically ranging between 180 to 200 degrees Celsius, 356 to 392 degrees Fahrenheit, ensuring that each biscuit is evenly baked to a golden brown. Advanced infrared sensors monitor the biscuits throughout the baking process, ensuring uniformity in color, texture, and moisture content. Once fully baked, the biscuits pass through a cooling tunnel that gradually reduces their temperature, preventing cracking or breakage. Next, the caramel layer is prepared. The caramel used in Twix bars is made from a precise blend of sugar, glucose syrup, milk, and butter. This mixture is heated in large stainless steel batch cookers, where it undergoes controlled caramelization. The temperature and cooking time are crucial in achieving the perfect consistency, thick enough to stay in place on the biscuit, but soft enough to deliver a smooth, chewy texture. Once the caramel reaches the desired consistency, it is transferred to a continuous depositor system. This machine evenly dispenses a uniform layer of caramel onto each biscuit. The caramel application must be carefully controlled to ensure consistency in thickness across all bars. Any inconsistencies could lead to difficulties in chocolate enrobing or affect the final texture. With the caramel applied, the bars move along the conveyor belt to a cooling station, where they pass through a controlled cooling tunnel. This tunnel gradually reduces the temperature of the caramel, allowing it to set properly while maintaining its soft, chewy texture. After cooling, the caramel-coated biscuits are ready for the enrobing process, where they will be covered in rich milk chocolate. The enrobing process is one of the most critical steps in Twix production. The milk chocolate coating is prepared in large conching machines, which continuously grind and refine cocoa mass, cocoa butter, sugar, and milk powder. This process enhances the texture and flavor of the chocolate, ensuring a smooth, creamy consistency. The chocolate is then tempered, a controlled heating and cooling process that stabilizes the cocoa butter crystals. Proper tempering is essential to achieving the signature glossy finish and preventing fat bloom, white streaks that can appear on improperly tempered chocolate. At the enrobing station, the caramel-topped biscuits pass through a continuous chocolate waterfall. This ensures that each bar is fully coated in an even layer of chocolate. Any excess chocolate is removed using controlled air jets and vibrating conveyors, which help distribute the chocolate evenly without excessive buildup. Some factories employ a two-stage enrobing process, where a thin base coat of chocolate is applied first to ensure better adhesion before the final, thicker chocolate layer is added. Once the bars are coated, they enter a multi-zone cooling tunnel. This tunnel is divided into different temperature zones that gradually reduce the temperature, allowing the chocolate to set perfectly without cracking or becoming dull. The bars emerge from the cooling tunnel with a firm, glossy chocolate coating, ready for the next stage of production. Quality control is a top priority at every stage of Twix production. After cooling, the bars pass through a series of automated inspection systems. High-speed vision cameras scan each bar for inconsistencies in chocolate coating, caramel distribution, and overall shape. Any bars that do not meet specifications are automatically rejected and sent for reprocessing. In addition to visual inspections, quality control teams conduct random weight checks, moisture analysis, and sensory evaluations to ensure that each batch meets Mars's stringent quality standards. Once the bars have passed inspection, they move to the packaging stage. Twix bars are individually wrapped using high-speed horizontal flow wrapping machines. These machines use heat-sealing technology to create airtight packaging that preserves freshness and prevents contamination. The wrapped bars are then grouped into multi-packs, which are sealed in branded cartons using automated case packing systems. After packaging, the final step in the process is palletization and distribution. Robotic palletizing systems stack the packaged bars onto pallets in precise arrangements, optimizing space for transport. The pallets are then shrink-wrapped for stability and loaded onto temperature-controlled trucks for distribution to retailers worldwide. Mars utilizes an advanced logistics network to ensure efficient delivery while maintaining product freshness. Throughout the entire production process, Mars adheres to strict food safety and sustainability standards. Each batch undergoes rigorous laboratory testing, including microbiological analysis, allergen testing, and texture verification. The company also invests in eco-friendly initiatives, such as reducing energy consumption in manufacturing and using recyclable packaging materials. Different Mars factories may employ slight variations in processing techniques based on regional ingredient availability and consumer preferences. For example, some regions may use alternative chocolate formulations with varying cocoa content, while others may adjust the caramel consistency based on market preferences. Additionally, limited edition Twix flavors, such as Twix white chocolate and Twix peanut butter, require modifications in ingredient formulation and processing techniques. As consumer demand for innovative flavors and healthier options grows, Mars continues to invest in research and development to improve Twix production. Recent advancements in AI-driven quality control, robotic automation, and sustainable ingredient sourcing are shaping the future of Twix manufacturing. Despite these innovations, the core principles of precision, consistency, and quality remain unchanged, ensuring that every Twix bar delivers the signature, crunchy, chewy, and chocolatey experience that consumers love. The making of a Hershey's chocolate bar is a complex, highly automated process that combines tradition with cutting-edge technology. From sourcing high-quality cocoa beans to wrapping the final product, every step is optimized for efficiency, consistency, and taste. The journey of a Hershey's bar begins with the careful selection of raw ingredients sourced from around the world. Cocoa, sugar, milk, and other ingredients are carefully tested to ensure they meet the company's high standards before they are transformed into the iconic chocolate bars that have been loved for generations. At the heart of every Hershey's chocolate bar is cocoa. The company sources its cocoa beans primarily from Ghana, Côte d'Ivoire, and Ecuador, regions known for producing high-quality beans with robust flavor profiles. Cocoa farmers in these areas harvest the ripe pods, extract the cocoa beans, and allow them to ferment for several days to develop their characteristic chocolatey taste. Once dried, the beans are shipped to Hershey's production facilities, where they undergo rigorous quality checks. Each shipment is tested for moisture content, flavor consistency, and the absence of contaminants. Only the highest quality beans make it through this stringent selection process. Once approved, the cocoa beans are sent to the roasting stage. Large industrial roasters expose the beans to carefully controlled heat, typically between 120 to 150 degrees Celsius, 248 to 302 degrees Fahrenheit, depending on the desired flavor profile. The roasting process is essential for developing the deep, complex flavors of chocolate. Different roasting profiles are used depending on whether the beans will be used for milk chocolate, dark chocolate, or other specialty products. After roasting, the cocoa beans enter the winnowing process. Specialized machinery cracks the roasted beans and removes the outer husks, leaving behind the valuable cocoa nibs. These nibs contain both the cocoa solids and cocoa butter needed for chocolate production. The nibs are then ground into a thick, dark paste known as chocolate liquor, which contains no alcohol despite its name. This chocolate liquor is the base for all Hershey's chocolate products. For Hershey's classic milk chocolate bars, chocolate liquor is combined with sugar, milk, and cocoa butter. The milk used in Hershey's chocolate is a key ingredient that gives it its distinctive taste. Unlike many European chocolates that use powdered or condensed milk, Hershey's uses fresh milk sourced from dairy farms in Pennsylvania and surrounding states. The milk is pasteurized and condensed before being blended with sugar to create a sweet, creamy base. The next stage in the process is refining. The chocolate mixture is run through a series of steel rollers that grind the particles to an ultra-fine consistency. This refining process is crucial for creating a smooth, melt-in-your-mouth texture. The finer the particles, the smoother the final chocolate will be. Once refined, the chocolate undergoes conching, a critical process that enhances flavor and texture. Conching machines, which resemble large industrial mixers, continuously stir the chocolate at controlled temperatures for several hours. This process aerates the chocolate, allowing unwanted acidic compounds to evaporate while enhancing its creamy mouthfeel. Hershey's uses a proprietary conching method that contributes to its signature flavor, which has a slightly tangy undertone due to controlled acidity in the milk. After conching, the chocolate moves to the tempering stage. Tempering is the process of heating and cooling chocolate in a precise manner to stabilize the cocoa butter crystals. Proper tempering ensures that Hershey's bars have a glossy finish, a firm snap, and a long shelf life. If the chocolate were not tempered correctly, it could develop fat bloom, a whitish streaking effect caused by unstable cocoa butter. Now, the tempered chocolate is ready for molding. Automated machines pour precise amounts of liquid chocolate into bar-shaped molds, which are then vibrated to remove air bubbles and ensure even distribution. The molds travel along a conveyor system into a cooling tunnel, where the chocolate solidifies into its final shape. Once cooled, the bars are ejected from their molds and transported via conveyor belts to the packaging area. Here, high-speed wrapping machines encase each bar in foil and branded paper sleeves, protecting the chocolate from moisture and light while ensuring a fresh, appealing presentation. Throughout the entire process, strict quality control measures are in place. High-resolution vision inspection systems scan each bar for defects, such as air bubbles, improper molding, or size inconsistencies. Bars that do not meet specifications are automatically rejected and sent for reprocessing. Additionally, random sensory evaluations are conducted by trained taste testers to ensure that the flavor, texture, and overall quality remain consistent. Once packaged, the final step is palletization and distribution. Automated robotic arms stack the packaged bars onto pallets, which are then shrink-wrapped for stability. These pallets are loaded onto temperature-controlled trucks and shipped to retailers worldwide. Hershey's operates an advanced logistics network that ensures timely delivery while maintaining product freshness. The entire manufacturing process is designed for efficiency, consistency, and sustainability. Hershey's continues to invest in eco-friendly initiatives, such as reducing water and energy consumption in production, using ethically sourced cocoa, and optimizing packaging materials to minimize waste. Different Hershey's factories may employ slight variations in processing techniques based on regional preferences and ingredient availability. Additionally, specialty products like Hershey's cookies and cream bars or Hershey's dark chocolate require modifications in ingredient formulation and processing times. As the chocolate industry continues to evolve, Hershey's remains at the forefront of innovation, combining tradition with advanced manufacturing techniques to produce its iconic chocolate bars. Through precision engineering, strict quality control, and a commitment to excellence, Hershey's ensures that every bar delivers the same beloved taste that generations have enjoyed. The making of Toblerone, the iconic triangular chocolate bar, is a masterclass in precision engineering, premium ingredient selection, and automated manufacturing processes. Unlike conventional chocolate bars, Toblerone stands out for its distinctive shape, rich Swiss milk chocolate, and the inclusion of honey and almond nougat. Every step, from sourcing the finest ingredients to molding the signature peaks, is meticulously controlled to ensure quality, consistency, and adherence to the Swiss chocolate making tradition. The process begins with sourcing high-quality ingredients. Toblerone's signature flavor comes from its carefully selected components: Swiss milk, sugar, cocoa mass, cocoa butter, honey, almonds, and egg whites. The milk, sourced from Swiss dairy farms, is a critical ingredient that contributes to the creamy texture. The cocoa is sourced from sustainable farms in Ghana and Ecuador, where beans are hand-harvested, fermented, and dried under strict quality control measures. Almonds are procured from select suppliers, ensuring they meet the required standards of size, flavor, and crunch. The honey, a key component that adds a subtle sweetness, is sourced from European beekeepers specializing in high-quality aromatic varieties. Once the ingredients arrive at the production facility, they undergo rigorous quality checks. Advanced spectroscopic analysis, moisture content testing, and flavor profiling ensure that each ingredient meets the brand's high standards. The cocoa beans are then roasted at carefully controlled temperatures to develop their deep, complex flavor. Different roasting profiles are used depending on whether the beans will be used for Toblerone's milk, dark, or white chocolate variations. After roasting, the cocoa beans move to the winnowing stage, where high-powered machinery cracks them open and removes the husks. The remaining cocoa nibs, which contain the essence of the chocolate, are then finely ground into a thick, rich paste known as chocolate liquor. This forms the base of Toblerone's chocolate. The chocolate liquor is blended with sugar, cocoa butter, and Swiss milk powder to create the signature, smooth and creamy chocolate mixture. The next step in the process is refining. The chocolate mixture passes through a series of heavy-duty steel rollers that break down the particles to an ultra-fine consistency. This is crucial in achieving the signature melt-in-your-mouth texture. The refining process also helps blend the ingredients evenly, ensuring a perfectly smooth mixture. Following refining, the chocolate undergoes conching, a process that enhances its texture and flavor. Large conching machines continuously mix, aerate, and heat the chocolate for several hours, allowing volatile acids to evaporate and the flavors to develop fully. Toblerone's conching process is fine-tuned to create a silky texture and a well-rounded, rich taste. Meanwhile, the honey and almond nougat mixture is prepared in a separate area of the factory. Sugar, honey, and egg whites are heated and aerated to create a light, chewy nougat. Almonds, which have been roasted to bring out their nutty aroma, are chopped into small pieces and folded into the nougat mixture. The nougat is then cooled and ground into fine pieces before being incorporated into the chocolate. Once the chocolate has completed the conching process, the finely ground nougat mixture is carefully folded into it, ensuring even distribution. This step is crucial in maintaining the signature texture and taste of Toblerone. With the chocolate and nougat mixture fully blended, the next stage is tempering. Tempering is a precise process of heating and cooling chocolate in a controlled manner to stabilize the cocoa butter crystals. Proper tempering ensures that the chocolate has a glossy finish, a firm snap, and a smooth texture. Toblerone's tempering process is carefully calibrated to achieve the ideal consistency before molding. Molding is where Toblerone's iconic shape comes to life. The tempered chocolate is poured into custom-designed triangular molds that give the bar its distinctive peaks. The molds are gently vibrated to remove air bubbles and ensure even distribution of the chocolate. After molding, the bars pass through a cooling tunnel where they are gradually cooled to allow the chocolate to set perfectly without cracks or imperfections. Once solidified, the bars are removed from the molds and transported to the quality control station. Each bar is inspected using high-resolution vision cameras, which detect any inconsistencies in shape, texture, or coating. Automated sorting systems remove any defective bars, ensuring that only perfectly shaped Toblerone bars proceed to packaging. The packaging process is designed to maintain the freshness and integrity of the chocolate. Toblerone bars are individually wrapped in foil to protect them from moisture and light, then placed into the iconic triangular cardboard cartons. High-speed packaging machines fold and seal the cartons with precision, ensuring that the bars remain securely enclosed. Following packaging, the bars are palletized using robotic systems, stacked carefully for stability during transport. These pallets are shrink-wrapped and loaded onto trucks for distribution to markets around the world. Temperature-controlled logistics ensure that the chocolate remains in perfect condition during transit. Throughout the entire manufacturing process, Toblerone maintains strict quality control measures. Each batch undergoes laboratory testing, including texture analysis, microbial screening, and taste assessments conducted by trained specialists. Data is continuously logged in automated tracking systems, allowing for full traceability of every Toblerone bar produced. Different Toblerone manufacturing facilities may employ slight variations in processing techniques depending on regional ingredient availability and market preferences. Specialty additions, such as Toblerone white chocolate or Toblerone dark, require slight modifications in ingredient formulations and processing steps. As consumer preferences evolve, Toblerone continues to innovate while maintaining the brand's heritage of Swiss chocolate craftsmanship. Investments in sustainable cocoa sourcing, eco-friendly packaging solutions, and advanced automation ensure that Toblerone remains a global favorite while reducing its environmental footprint. Through precision engineering, time-honored techniques, and a commitment to quality, every Toblerone bar delivers the signature taste and texture that chocolate lovers around the world cherish. The production of Snickers, one of the world's most popular chocolate bars, is a highly automated and meticulously controlled process designed for efficiency, consistency, and large-scale output. With its signature combination of nougat, caramel, peanuts, and milk chocolate, Snickers is produced in state-of-the-art facilities that use cutting-edge food processing technology, ensuring that every bar meets the brand's high-quality standards. From sourcing the finest raw ingredients to packaging and distribution, every step is optimized to deliver the same taste, texture, and satisfaction in every bite. The journey of a Snickers bar begins with the careful selection of raw materials. The main components include sugar, peanuts, milk powder, cocoa mass, cocoa butter, palm oil, glucose syrup, egg whites, and emulsifiers. These ingredients are sourced from carefully vetted suppliers, ensuring compliance with strict food safety and sustainability standards. Mars, the company behind Snickers, prioritizes responsible ingredient sourcing, ensuring that cocoa is ethically obtained through its Cocoa for Generations program. which promotes fair labor practices and sustainable farming methods. Peanuts, another crucial ingredient, are primarily sourced from the United States, where they are grown under controlled conditions to maintain size, flavor, and crunch. Once the ingredients arrive at the manufacturing facility, they undergo a rigorous quality control process. Each batch is tested for moisture content, purity, and potential contaminants. Peanuts, in particular, go through an additional inspection phase, where they are sorted by size and quality. High-speed optical sorting machines remove any defective or discolored peanuts, ensuring that only the best nuts make it into Snickers bars. The first major step in the Snickers production process is creating the nougat base. Nougat provides the chewy texture that forms the foundation of the bar. It is made by combining sugar, corn syrup, and water, which are heated in large industrial cooking vats to create a syrup. This syrup is then aerated using high-powered whipping machines, which incorporate fine air bubbles, giving the nougat its characteristic light and chewy texture. Egg whites or soy protein are added as stabilizers to help maintain consistency. Once aerated, the nougat is spread onto a moving conveyor belt in a continuous sheet, where it is allowed to cool and set. This process is carefully controlled to prevent the nougat from becoming too hard or too soft. Automated guillotine cutters then slice the nougat sheet into uniform rectangular portions, ensuring that each piece is the exact size required for Snickers bars. Next comes the caramel layer. The caramel in Snickers is made from a blend of sugar, glucose syrup, milk, and butter, which is heated in large stainless steel batch cookers. The temperature is carefully monitored to achieve the perfect viscosity, thick enough to hold its shape, but soft enough to provide a smooth, chewy texture. Once cooked to perfection, the caramel is poured in a controlled stream onto the nougat base. The caramel-covered nougat passes through a cooling tunnel, where it sets just enough to be firm, but still pliable. Now it's time to add the peanuts. Before being incorporated into the bars, the peanuts are roasted in industrial ovens to enhance their flavor and crunch. After roasting, they are cooled and evenly distributed over the caramel layer using precision peanut dispensers. These machines ensure that each bar receives the right amount of peanuts, maintaining uniformity across all Snickers bars. Once the peanuts are in place, the layered nougat, caramel, and peanut sheet moves to the cutting stage. High-speed rotary blades slice the continuous sheet into individual bar-sized portions. Each cut must be precise, ensuring that the caramel and nougat layers remain intact while maintaining a consistent size. The next critical step is chocolate enrobing. The milk chocolate coating used for Snickers bars is made from a blend of cocoa mass, cocoa butter, sugar, and milk powder. This mixture is refined and conched in large machines that continuously grind the chocolate to achieve a smooth texture. The chocolate is then tempered, a process that involves controlled heating and cooling to stabilize the cocoa butter crystals. Proper tempering ensures a glossy finish and prevents fat bloom, which can cause chocolate to develop a dull appearance. At the enrobing station, the cut bars pass through a waterfall of liquid milk chocolate, fully coating them. Excess chocolate is removed using controlled air jets and vibrating conveyors, ensuring an even layer without excessive buildup. Some factories use a two-stage enrobing process, where a thin base coat of chocolate is applied first to create a stable foundation before the final. Thicker chocolate layer is added. After enrobing, the bars enter a multi-zone cooling tunnel. This tunnel gradually lowers the temperature in controlled stages, allowing the chocolate to set properly without developing cracks or dull spots. Once fully cooled, the Snickers bars emerge with a perfectly solidified chocolate coating, ready for quality inspection. Quality control is a critical component of Snickers production. Each bar undergoes a series of automated inspections to ensure that it meets strict specifications. High-speed vision inspection systems equipped with high-resolution cameras, scan each bar for defects such as uneven coating, improper size, or misshapen layers. Any bars that do not meet the required standards are automatically rejected and sent for reprocessing. Additional quality checks include weight verification, moisture content analysis, and sensory testing conducted by trained specialists. Once the bars have passed inspection, they move to the packaging stage. Snickers bars are individually wrapped in plastic film using high-speed horizontal flow wrapping machines. These machines use heat sealing technology to create airtight packaging that preserves freshness and prevents contamination. The wrapped bars are then grouped into multi-packs and packed into branded cartons using automated case packers. The final step in the process is palletization and distribution. Automated systems stack the packaged cartons onto pallets in precise formations, optimizing space for transport. These pallets are then shrink-wrapped for stability and loaded onto temperature-controlled trucks for distribution to retailers worldwide. Snickers bars are shipped to over 70 countries, requiring an advanced logistics network to ensure that they arrive fresh and in perfect condition. Throughout the entire production process, Mars maintains stringent food safety and sustainability practices. Each batch undergoes extensive laboratory testing, including microbiological screening, allergen testing, and texture verification. The company also invests in sustainable ingredient sourcing, reducing its environmental footprint through energy-efficient manufacturing processes and eco-friendly packaging solutions. Different Snickers manufacturing facilities may employ slight variations in processing techniques based on regional ingredient availability and consumer preferences. For example, some regions may use alternative chocolate blends with varying cocoa content, while others may modify the nougat or caramel consistency based on market demands. Additionally, special edition Snickers bars, such as Snickers Almond or Snickers Peanut Butter, require modifications in ingredient formulation and production methods. As consumer preferences evolve, Mars continues to innovate while maintaining the classic Snickers taste and texture. Advancements in automation, AI-driven quality control, and sustainable manufacturing practices are shaping the future of Snickers production. Despite these innovations, the fundamental principles of precision, consistency, and quality remain unchanged, ensuring that every Snickers bar delivers the same delicious combination of chewy nougat, gooey caramel, crunchy peanuts, and smooth milk chocolate that has made it a favorite among chocolate lovers worldwide. The production of Tony's Chocolonely chocolate bars is a carefully designed process that emphasizes ethical sourcing, sustainability, and high-quality chocolate-making techniques. Unlike traditional chocolate brands, Tony's Chocolonely is dedicated to creating a slave-free chocolate industry, ensuring that every step in the supply chain is transparent and fair. From sourcing cocoa beans from cooperatives in West Africa to molding and packaging the final bars, the production process is a seamless blend of traditional craftsmanship and modern automation. The journey of a Tony's Chocolonely bar begins with cocoa sourcing. The company partners with cooperatives in Ghana and Côte d'Ivoire, regions that are known for cocoa production, but also face significant challenges related to child labor and unfair wages. Tony's Chocolonely implements direct trade practices, paying a premium for cocoa and providing additional support to farmers through training programs and financial resources. This ensures that the beans are ethically sourced while maintaining a high standard of quality. Once harvested, the cocoa beans go through a meticulous post-harvest process. Farmers ferment the beans for several days, a crucial step that develops the deep, complex flavors needed for premium chocolate. After fermentation, the beans are spread out under the sun to dry, reducing moisture content and preventing mold growth. When dried to the appropriate level, the beans are packed into jute sacks and shipped to Tony's Chocolonely's processing facilities. Upon arrival at the factory, the beans undergo rigorous quality control checks. Samples from each shipment are tested for moisture levels, flavor consistency, and potential contaminants. Beans that pass inspection are stored in climate-controlled silos to maintain freshness before entering the production line. The first step in the chocolate making process is roasting. Large industrial roasting machines heat the beans at precise temperatures, usually between 120 to 150 degrees Celsius, 248 to 302 degrees Fahrenheit. This process enhances the natural chocolate flavors and eliminates unwanted bitterness. The roasting time and temperature depend on the type of chocolate being produced. Dark chocolate requires a slightly longer roasting process than milk chocolate to develop its rich, bold flavors. Once roasted, the beans enter the winnowing process. A specialized machine cracks open the roasted beans and removes the outer husks, leaving behind the valuable cocoa nibs. These nibs contain both cocoa solids and cocoa butter, the essential components of chocolate. The nibs are then ground into a thick, smooth paste known as chocolate liquor. This process, carried out by industrial grinders, reduces the particle size of the nibs, creating a velvety consistency. At this stage, different chocolate variations begin to take shape. For Tony's Chocolonely's milk chocolate bars, the chocolate liquor is combined with sugar, milk powder, and additional cocoa butter to create a creamy texture. For dark chocolate, higher cocoa percentages are used with less sugar and no milk. The next step in the process is refining. The chocolate mixture is passed through heavy-duty steel rollers that grind the ingredients into ultra-fine particles. This step is crucial for achieving the smooth texture that defines high-quality chocolate. The finer the particles, the better the melt-in-your-mouth experience. Following refining, the chocolate undergoes conching, a process that enhances both texture and flavor. Large conching machines continuously mix and aerate the chocolate for several hours, allowing any residual acidity to evaporate while intensifying the chocolate's richness. The conching time varies depending on the desired flavor profile. Longer conching results in a smoother, more developed taste. After conching, the chocolate is tempered, a precise heating and cooling process that stabilizes the cocoa butter crystals. Proper tempering ensures that Tony's Chocolonely bars have a glossy finish, a satisfying snap when broken, and a long shelf life without developing fat bloom, the white streaks that can appear on improperly tempered chocolate. Once tempered, the liquid chocolate is ready for molding. Unlike most chocolate bars, Tony's Chocolonely bars are intentionally molded in an uneven pattern, symbolizing the unequal distribution of wealth in the chocolate industry. Automated machines pour precise amounts of chocolate into these custom-designed molds, which are then gently vibrated to remove air bubbles and ensure even distribution. The molds are then transferred to a cooling tunnel, where the chocolate gradually solidifies under controlled temperatures. This process prevents the bars from developing surface defects and ensures that they retain their perfect shape. Once the chocolate has fully set, the bars are ejected from the molds and sent to the quality control station. High-speed vision inspection systems scan each bar for defects, such as air bubbles, improper molding, or uneven texture. Any bars that do not meet the required standards are removed from the production line and either reprocessed or discarded. After passing quality checks, the bars move to the packaging stage. Tony's Chocolonely uses brightly colored, easily recognizable wrappers, each featuring bold typography and branding. The packaging process is fully automated, with high-speed wrapping machines, sealing each bar in foil and paper to protect it from moisture and contamination. The wrapped bars are then packed into cartons using robotic case packers. The final step in the process is palletization and distribution. Automated robotic systems stack the packaged bars onto pallets in a precise arrangement, optimizing space for transport. Manufacturing Almond Joy candy bars on an industrial scale begins long before any chocolate is melted or coconut is mixed. It starts with the careful sourcing and preparation of one of the candy's most iconic and defining components, the coconut. This isn't just any shredded coconut. This is a specific, moisture-balanced, finely textured variety that gives Almond Joy its distinct chewy center. Producing coconut to these specifications requires a highly controlled and deliberate process. And in modern facilities, this step alone involves extensive coordination between agricultural suppliers, food scientists, and processing engineers. The coconuts used in Almond Joy bars are primarily sourced from tropical regions like the Philippines, Indonesia, and India, where coconut palms grow in warm, humid climates and are harvested multiple times per year. The coconuts are selected based on strict criteria such as maturity, size, and oil content, all of which contribute to the flavor and structure of the final product. After harvesting, the outer husks are mechanically removed using rotary dehusking machines, exposing the inner brown shells. These shells are then cracked open using high-torque hydraulic presses or mechanical splitters, allowing access to the white coconut meat inside, also known as copra. Once separated from the shell, the coconut meat is washed in large stainless steel tanks using filtered water, sometimes with a light chlorine solution to remove any contaminants, shell fragments, or residual dirt. The clean coconut meat is then graded using high-speed rotary shredders, which reduce it into uniform strands. These industrial shredders operate at several thousand RPMs and are fitted with specialized blades designed to achieve a consistent flake size. The exact dimensions of the shredded coconut are critical. Too coarse, and the texture becomes stringy. Too fine, and it loses its chewiness. The shredded product is then passed through vibratory sieves to remove any oversized or undersized particles, ensuring each flake meets factory specifications. Once the coconut is shredded and sized, it undergoes a drying phase, designed not to fully desiccate the coconut, but to bring its moisture content into a very specific range, typically between 12 and 14%. This drying process is carried out in large belt dryers or fluidized bed dryers that blow heated air over the coconut shreds while keeping them suspended and moving, ensuring even drying throughout. Sensors embedded in the dryer constantly monitor moisture levels in real time, allowing for micro adjustments to airflow and temperature. This precision ensures that the final coconut retains its soft, moist chewiness without being wet or prone to microbial spoilage. Once dried, the coconut is cooled with ambient air and sent through a metal detection system before being packed into sterile bulk totes or drums, ready to be delivered to the candy production line. Now it's time to go into the coconut syrup blending process, where the prepped coconut is transformed into the moist, sweet filling that forms the base of every Almond Joy bar. At this stage, the dried coconut shreds are transferred from storage bins into large stainless steel ribbon blenders or planetary mixers. These mixers are food grade and designed to gently fold the ingredients together without compressing or overworking them, which would damage the texture. While the coconut is being added to the mixer, a separate part of the factory is simultaneously preparing a sugar syrup that will serve as the binder and sweetener. This sugar syrup is cooked in large steam-jacketed kettles, each fitted with agitators and temperature sensors. The syrup typically contains a blend of sucrose, corn syrup, and a small percentage of invert sugar, which helps prevent crystallization and keeps the final mixture smooth and cohesive. The ingredients are combined with water and brought to a boil, then held at a precise temperature of around 230 to 240 degrees Fahrenheit. Once the syrup reaches the desired consistency and viscosity, it is pumped through insulated transfer lines into the mixers containing the shredded coconut. The hot syrup is slowly added into the mixing chamber while the paddles rotate at a controlled speed, ensuring that every strand of coconut becomes evenly coated. This mixing step is closely monitored for torque resistance, an indirect measure of viscosity and saturation. If the mixture becomes too stiff, it indicates that not enough syrup has been added, while an overly slack consistency could suggest too much moisture. Adjustments are made in real time, either by slowing down the mixing blades or by adding additional syrup in carefully measured quantities. The end result is a glossy, dense, and aromatic coconut mixture with a smooth mouthfeel and a controlled stickiness that allows it to hold together when molded. This freshly prepared filling is discharged from the mixer into temperature-controlled holding hoppers. From there, it is fed through sanitary auger systems into the forming line, where the next phase of production begins, shaping each bar's core. But up next is the forming process, where this cohesive coconut mixture is portioned and molded into the rectangular log shape that defines the inner core of every Almond Joy. This step is handled by a specialized extrusion and forming system. The mixture is continuously extruded through a die system that determines the width and height of the log. These forming dies are custom designed for Almond Joy and produce a consistent cross-section with slightly rounded tops, ensuring a uniform bite and a reliable surface for almond placement. The extrusion head releases a continuous ribbon of coconut mixture onto a moving conveyor belt, and a high-speed rotary guillotine, timed with the conveyor's speed, cuts this ribbon into individual bar-length pieces. The distance between each cut is controlled down to the millimeter, and a sensor-based feedback system ensures that every bar is exactly the same size. After cutting, a short air blast is applied to each log to clear away any stray coconut flakes and ensure clean edges. As the bars are cut, they enter a cooling conveyor that travels through a tunnel kept at approximately 45 degrees Fahrenheit. The cooling process is essential at this point. Not only does it help the bars hold their shape, but it also stabilizes the sugar syrup binder so that the mixture doesn't slump or deform in the next step. A key consideration during this cooling stage is air humidity. If the environment is too dry, the coconut can begin to crust or dry out. Too humid, and condensation may form, which can affect downstream adhesion with the chocolate coating. For this reason, industrial humidity control units maintain relative humidity levels around 45 to 55% inside the cooling tunnel. Once cooled and firmed, the coconut logs are transferred by conveyor to the almond placement system. Each log must receive exactly 2 whole almonds, neither more nor less, positioned evenly across the top surface. The almonds used in this process are themselves the result of a careful preparation sequence. Raw almonds are sourced from large-scale growers, often in California, and are received at the factory in bulk containers. These almonds are sorted, cleaned, and then dry roasted in large convection ovens. Roasting enhances flavor, reduces moisture to less than 5%, and gives the almonds the crunch consumers expect. After roasting, the almonds are cooled and transported to a hopper above the placement system. Here, they are singulated, separated into single file, and guided into individual almond placement arms. These arms are controlled by a vision-guided robotic system that tracks the position of every coconut log in real time. Using photoelectric sensors and high-resolution cameras, the system places each almond with millimeter-level accuracy on top of the log. The almonds are pressed into the surface just enough to adhere without sinking, and an inline inspection system checks that every bar has precisely 2 almonds aligned correctly. Any bar that deviates from this standard is removed from the line for manual inspection or rework. Now it's time to go into the chocolate enrobing stage, which marks the beginning of the transformation from a basic assembly of ingredients into the finished, glossy, consumer-ready candy bar. This process involves fully coating the almond-topped coconut cores with a layer of milk chocolate. But this is no ordinary chocolate. It has been specifically formulated and tempered to provide the right snap, shine, and melt-in-the-mouth texture that defines the Almond Joy eating experience. The chocolate is stored in holding tanks maintained at 110 to 115 degrees Fahrenheit and stirred continuously to ensure it remains fluid and free from separation. Before use, the chocolate is tempered through a process that heats, cools, and reheats it to align the cocoa butter crystals in a stable form. Proper tempering is essential as it prevents fat bloom and gives the coating its glossy finish and clean break. The tempered chocolate is pumped into an enrobing machine, which dispenses it in a continuous curtain across the width of the conveyor belt. As the coconut and almond cores pass underneath, they are fully submerged in the falling sheet of chocolate, while a bottoming unit applies a layer of chocolate to their underside. Immediately afterward, a series of air blowers remove excess chocolate, ensuring a uniform thickness and revealing the shape of the almonds beneath. What emerges is a fully coated bar that looks and feels like the final product, but still needs time to set. That step begins as the bars enter a temperature-controlled cooling tunnel, and that's where the next phase begins. Inside the cooling tunnel, a meticulously engineered, climate-controlled chamber extending over 30 feet in length, the freshly enrobed Almond Joy bars begin their chocolate setting phase. This tunnel is one of the most crucial parts of the process, ensuring that the tempered chocolate coating transitions from a glossy liquid into a solid shell with the perfect texture and finish. The chocolate must cool at a precise rate, not too fast, which could result in cracking or sugar bloom, and not too slowly, which could cause the cocoa butter crystals to misalign, leading to dullness or fat bloom on the surface. The tunnel operates at an ambient temperature between 45 and 55 degrees Fahrenheit, and relative humidity is tightly controlled around 50%. High-efficiency fans circulate cold air evenly across all bars on the conveyor, and temperature sensors track minute variations along the length of the tunnel. The speed of the conveyor is carefully synchronized with the chocolate's crystallization curve so that the bars spend just the right amount of time cooling, usually between 7 and 12 minutes, depending on environmental conditions, line speed, and chocolate thickness. During this stage, the chocolate coating fully hardens around the coconut and almond core, creating a glossy, smooth outer layer that locks in moisture and flavor. The almonds, having been gently pressed into the top of the coconut before enrobing, remain clearly visible through the chocolate shell, creating the bar's iconic bumpy silhouette. As the bars exit the tunnel, they are now fully formed, with all primary ingredients integrated and stabilized. But the next phase, inspection and quality control, ensures that only perfect bars make it into the hands of consumers. The next step is the multi-layered inspection and quality assurance phase, a critical junction in the Almond Joy manufacturing process. Here, each fully cooled, enrobed bar passes under a series of digital scanning systems equipped with high-resolution cameras and sensors that detect inconsistencies in shape, size, and appearance. These systems analyze every bar in real time using image recognition algorithms trained to identify surface defects, incomplete chocolate coverage, missing almonds, or any signs of misalignment. Each camera system captures dozens of images per second, creating a detailed digital fingerprint of each bar. If a defect is detected, such as an air bubble on the surface, a chocolate smear, or a misaligned almond, the bar is automatically rejected using a quick puff of compressed air that directs it off the main conveyor into a designated collection tray. Rejected bars are recorded and analyzed in quality control logs to monitor trends and flag any upstream issues in real time, like syrup inconsistencies or almond placement variances. Following the visual inspection, the bars pass through an inline check weighing station. This precision balance system measures the mass of each individual bar down to the 1/10 of a gram. Bars that are even slightly under or overweight are flagged and rejected from the line. This strict weight control not only ensures product consistency and consumer satisfaction, but also regulatory compliance, as all packaged goods must meet labeled net weight declarations. These check weighers are recalibrated frequently during production to maintain absolute accuracy, and the results are logged digitally to provide traceable batch records. Next, a random sampling process is initiated where trained human inspectors pull sample bars from the line every few minutes. These samples are taken to a nearby quality assurance room for deeper evaluation. Inspectors slice open the bars and examine the cross-section for proper ingredient distribution, moisture retention in the coconut layer, almond placement, and shell integrity. Taste testing is performed by a trained sensory panel in a separate tasting room to ensure the flavor profile remains consistent. Parameters like sweetness, chewiness, and chocolate snap are all evaluated and recorded in a detailed quality report. Once bars have successfully passed through the inspection phase, they are ready for the next stage, packaging. But up next is the flow wrapping process, where each Almond Joy bar is individually wrapped using high-speed machinery designed to maintain hygiene, preserve freshness, and uphold branding consistency. The packaging film, pre-printed with the Almond Joy logo and product information, is loaded in giant rolls at the start of the packaging line. These rolls are threaded through a series of rollers and tensioners that keep the film aligned and taut as it's fed into the wrapping unit. The bars are spaced and synchronized onto a conveyor lane and fed into the flow wrapping machine, which envelopes each one in film and seals it at the sides and ends using heated crimping jaws. These jaws press the film together and apply controlled heat and pressure to create airtight seals that are strong yet easy to open. The sealing temperatures are carefully monitored to avoid overheating the chocolate within, as excess heat could cause the surface to dull or soften. Each wrapped bar is then passed under a thermal inkjet or laser coder, which prints the best before date, batch code, and production time directly onto the wrapper. This traceability information is vital in case of recalls, inventory tracking, or shelf life analysis. Vision sensors verify the presence and clarity of the code, and any missing or illegible codes trigger a rejection mechanism. The speed of this entire process is remarkable. Modern flow wrappers can handle upwards of 500 bars per minute, all synchronized perfectly to match the upstream enrobing output. Once wrapped and coded, the Almond Joy bars are grouped into retail-ready formats. Depending on the destination, this could mean twin packs, king-size versions, or standard singles in cartons. Cartoning machines fold and glue cardboard sleeves or cartons, then insert the correct number of bars automatically. These cartons are scanned for correct orientation, closed, and labeled with shipping and SKU data. A final check weigher ensures that the total weight of each carton falls within specification, and the completed units are then moved down the line to case packing. The case packing phase involves automated robotic arms or pick-and-place systems that lift finished cartons and place them into larger, corrugated shipping cases. The arrangement within each case is optimized for pallet stability and protection during transit. Each case is labeled with product identifiers, batch codes, and destination information, then sealed and conveyed to a palletizing station. Palletizing robots stack the cases onto wooden or plastic pallets in precise configurations to maximize space and maintain structural integrity during transport. Once a full pallet is assembled, it's wrapped in high tensile stretch film using automated rotary arm or turntable wrappers. This wrapping secures the load against shifting during transportation and also provides a barrier against dust and moisture. Each pallet is then tagged with a barcoded shipping label that includes tracking information, weight, and customer-specific handling instructions. The completed pallets are moved to a climate-controlled storage area within the warehouse to await shipment. Now, it's time to go into the logistics and distribution stage, where the focus shifts from production to coordinated movement and inventory management. Almond Joy bars, like all Hershey's products, are managed within an enterprise resource planning system that tracks production batches, inventory turnover, and customer orders in real time. Based on demand forecasts, pallets are selected for outbound shipment, assigned to specific trucks or containers, and scanned out of the warehouse with full digital traceability. Transport is typically handled using refrigerated trucks during warmer months, as the milk chocolate in Almond Joy bars is sensitive to heat. Temperatures are maintained between 55 and 65 degrees Fahrenheit during transit, and GPS-linked thermologgers monitor each vehicle's internal climate from origin to delivery. If a truck deviates from its safe range, alerts are sent to both logistics managers and warehouse supervisors to prevent spoilage. Once the bars reach regional distribution centers or retail warehouses, the product is scanned into inventory and routed to store shelves. Retail partners rely on synchronized inventory systems that replenish stock as it sells, often based on point-of-sale data. The entire journey, from coconut grove to grocery store, can be completed in just a matter of weeks, but every phase must function flawlessly to deliver a bar that meets Hershey's standards for quality, freshness, and consistency. And even once the product hits shelves, the factory's job isn't done. Ongoing consumer feedback, seasonal demand changes, and promotional cycles influence continuous adjustments in batch sizes, production schedules, and packaging variations. Special holiday versions, multi-packs, and limited time offers are all planned months in advance and require tailored processes, new molds, and reprogrammed machinery, an impressive level of flexibility embedded within an otherwise standardized production system. Quality assurance continues to play an active, ongoing role in the manufacturing of Almond Joy, even after the bars have been wrapped, packed, and prepared for distribution. In fact, behind the scenes of the main production line, a parallel infrastructure operates continuously to monitor, record, and validate every element of the process in real time and long after the initial production phase. This includes not only in-process checks, but detailed post-production sampling and retention, which are central to traceability, regulatory compliance, and product consistency. One critical ongoing practice is the archiving of batch samples. As bars are wrapped and prepared for shipment, dedicated staff routinely pull random samples from each batch, often one every few thousand bars. These samples are sealed, labeled, and logged with all relevant metadata: the exact time of production, line number, raw material codes, chocolate viscosity at time of enrobing, coconut moisture content, and even almond roast profiles. These reference bars are stored in secure, climate-controlled storage units maintained at conditions that mimic ideal shelf environments. The goal is to preserve these products in a stable state for up to 2 years, during which time they may be retrieved for comparison if any quality concerns or deviations arise. In addition to acting as an insurance policy against customer complaints or distributor queries, these archived samples are regularly tested as part of long-term shelf life studies. Trained quality assurance technicians perform controlled aging studies by artificially accelerating the aging process in heated chambers to evaluate how the product will hold up over time. These studies track changes in coconut chewiness, chocolate bloom resistance, almond crunch retention, and overall flavor integrity. Sensory analysis is conducted by expert panels who evaluate sweetness, aroma, textural contrast, and mouthfeel using standardized scoring systems. This data feeds back into ingredient sourcing decisions and packaging refinements, allowing the team to adjust variables well before any potential issues could reach consumers. Now, it's time to go into the digital control systems that operate silently beneath every piece of equipment, coordinating, recording, and adjusting every stage of the Almond Joy production process. At the core of this system is a network of programmable logic controllers, PLCs, which manage the real-time operation of machinery across the factory floor. These industrial computers are programmed to respond to sensor inputs and control outputs with extreme precision, enabling the synchronization of critical events such as syrup dosing, coconut extrusion, chocolate tempering, and wrapper sealing. For example, if the syrup temperature in the blending kettle falls even slightly below the optimal range of 235 to 240 degrees Fahrenheit, the PLC will automatically trigger a compensatory adjustment in steam pressure. Similarly, if a sensor detects that the chocolate curtain in the enrober has begun to thin, indicating an issue with flow rate or chocolate viscosity, the system can alter pump speed, activate an agitator, or send an alert to the line technician. These reactions happen in milliseconds, ensuring seamless operation with minimal human intervention. All this data funnels into a supervisory control and data acquisition system, or SCADA, which acts as the digital nervous system of the plant. SCADA systems provide centralized visualization of every variable in production, from torque readings in the coconut mixes to conveyor belt speeds on the packaging line. Live dashboards display real-time metrics alongside historical trends, and operators can set control limits to trigger alarms, shutoffs, or automatic corrective actions when deviations occur. Data logging is continuous, with every action time-stamped and stored in redundant backups for audit and analytics purposes. But up next is the role of continuous improvement teams and how they use this wealth of production data to fine-tune the manufacturing process. Rather than viewing each shift as a discrete operation, modern Almond Joy factories treat every minute of production as a learning opportunity. Statistical process control specialists and lean manufacturing engineers analyze massive volumes of data to identify small but significant trends. For instance, if there's a subtle uptick in the rate of chocolate flow variation on line 2 during evening shifts, it might suggest thermal drift in the tempering unit or minor calibration errors in the chocolate pump. These insights allow preventive maintenance schedules to be updated, saving time and resources while minimizing the risk of future disruptions. Some adjustments are made on the spot, while others lead to full pilot testing cycles. Pilot lines, scaled-down versions of the full production setup, allow engineers to test adjustments to temperature profiles, mixing durations, or conveyor speeds without interrupting primary operations. For example, if a new batch of coconut arrives with slightly higher fat content than normal, the pilot team may experiment with modified syrup ratios or mixing times to maintain the same moisture binding characteristics. Results are measured using laboratory tools like refractometers, rheometers, and moisture analyzers. And the most successful configuration is then rolled out to full production. The focus on fine-tuning doesn't stop at equipment and ingredients. It also extends to the behavior of the product throughout the supply chain. Some Almond Joy bars are shipped across the country or even internationally, and that means packaging and formulation must perform under a wide range of conditions. Engineers perform transit simulations using vibration tables and thermal chambers to replicate the effects of long-distance trucking or air freight. These simulations allow packaging specialists to evaluate wrapper integrity, seal strength, and chocolate stability under heat and motion stress. In cases where performance can be improved, new materials or layering structures are proposed, often months before the consumer ever sees the final package. It all begins with the careful sourcing and intake of raw chicken, a process that is both biologically sensitive and highly mechanized to maintain consistent quality and food safety. The chickens destined for KFC facilities are selected from specific poultry farms that follow stringent guidelines set by both KFC's corporate standards and local regulatory bodies. These farms raise broiler chickens, a breed specifically developed for rapid growth and high meat yield, particularly in the breast and thigh areas. To ensure consistency in texture and flavor, the birds are typically grown under controlled feeding regimens with strict monitoring of their diet, environment, and health status from hatchery to harvest. Once the birds reach the appropriate weight and age, usually between 5 to 7 weeks, they are transported live in temperature-regulated, well-ventilated trucks to the processing facility. Upon arrival, the birds are unloaded through an automated conveyor system and transferred to a staging area that uses dim lighting and gentle sound cues to keep the animals calm. This pre-processing environment is crucial for maintaining meat quality, as high stress can cause conditions like pale, soft, and exudative meat, or dark, firm, dry meat, which are both unsuitable for KFC's strict quality requirements. The first critical step in the factory is stunning, which is done using controlled atmosphere stunning, a method that introduces carbon dioxide in gradually increasing concentrations to render the chickens unconscious. This technique is widely considered more humane and helps preserve the quality of the meat. Once the birds are unconscious, they move to the next stage, where an automated system makes a precise incision to the neck, ensuring rapid and thorough bleeding. The bleeding process is closely timed and monitored using sensors and timers to maximize the efficiency of blood removal, which is essential not only for meat appearance and shelf life, but also for meeting food safety regulations. Following exsanguination, the birds proceed through a high-capacity scalding tank filled with water heated to approximately 60 degrees Celsius. This stage loosens the feathers by relaxing the collagen in the feather follicles. The duration and temperature are controlled to a fine margin to ensure that the skin is neither overcooked nor damaged. After scalding, the birds are transferred into rotary feather pluckers, drum-shaped machines lined with soft rubber fingers that rotate at high speeds. These fingers remove feathers through a gentle abrasive action. Any residual feathers, particularly around the wings and tail, are removed by additional targeted plucking devices or hand finishing stations, depending on the processing line speed and factory setup. The next step is evisceration, a highly mechanized process involving robotic arms and vision-guided machinery. The system first makes a precise incision along the abdominal cavity before extracting the internal organs. This includes the heart, liver, gizzard, and intestines, which are separated into byproduct streams for different uses or disposal. Each carcass is inspected by high-speed cameras equipped with AI-powered image recognition software to detect any abnormalities such as bruising, discoloration, or contamination. Chickens that fail this inspection are automatically diverted from the production line for further examination or removal. This real-time quality assurance technology helps maintain a consistent and safe supply of chicken for further processing. Now it's time to move on to the chilling process, which is absolutely vital for halting bacterial growth and ensuring a clean transition from slaughter to further cutting and seasoning. KFC factories typically use an immersion chilling method, where eviscerated chickens are conveyed through long stainless steel tanks filled with chlorinated cold water, maintained at around 0 to 4 degrees Celsius. The flow of water is designed in a countercurrent pattern, meaning the cleanest water contacts the most recently added chickens, ensuring optimal hygiene. This step rapidly reduces the internal temperature of the chicken from roughly 40 degrees Celsius to below 4 degrees within an hour, thereby locking in freshness and significantly extending the shelf life of the meat. After chilling, the carcasses proceed to the cutting and portioning stage. This part of the process is perhaps one of the most intricate in the factory. Specialized rotary cutting machines equipped with lasers and 3D scanners assess the size and density of each chicken in real time. Based on this data, programmable robotic blades segment the carcasses into uniform cuts: legs, thighs, wings, breasts, and keels. Each piece is sized to match strict dimensional and weight criteria, which are crucial for ensuring consistent cooking times and presentation across all KFC restaurants worldwide. The system is calibrated to yield the optimal number of each type of piece from every bird, reducing waste and maximizing efficiency. If a cut doesn't meet the precise size range, it is automatically redirected for use in alternative products like tenders or popcorn chicken. The next phase focuses on marination, a process that introduces moisture, flavor, and functional ingredients into the chicken to enhance both taste and texture. Once portioned, the chicken pieces are loaded into massive stainless steel tumblers, each capable of holding hundreds of kilograms of product. Inside the tumbler, a proprietary liquid marinade blend is introduced. While the exact formulation is a closely guarded secret, the marinade typically includes salt, phosphate-based tenderizers, flavoring agents, and sometimes buttermilk solids to create the tender, juicy interior that KFC is known for. The tumbling action lasts anywhere from 15 to 30 minutes, depending on the batch size and desired intensity. And the drum rotates on multiple axes to ensure that every surface of every piece of chicken is exposed to the marinade. This mechanical agitation also helps the meat fibers absorb the liquid more thoroughly, contributing to the product's juiciness even after high temperature frying. But up next comes the breading stage, which is arguably the most iconic part of KFC's production process. After marination, the chicken is gently drained and transferred to the breading stations, where each piece is coated in the proprietary blend of flour and seasoning, known famously as the 11 herbs and spices. To replicate the hand-breaded quality that KFC is known for, even at industrial scale, specialized breading drums are used. These drums simulate the hand-tossing action by gently rolling the chicken pieces in the seasoned flour, while pneumatic paddles and vibration systems ensure that every crevice is fully coated. At this point, moisture content is carefully controlled to ensure adhesion without creating clumps or overly moist surfaces, which would ruin the crispy texture during frying. Once breaded, the chicken moves immediately to the par frying or pre-frying stage. This step is critical for setting the breading so it doesn't fall off during full cooking at the restaurant. The breaded pieces are passed through continuous fryers filled with hot oil maintained at temperatures between 170 to 180 degrees Celsius. In this stage, the chicken is fried for a short duration, usually 90 to 120 seconds, just enough to solidify the coating and begin the Maillard reaction, which is responsible for the development of flavor and the golden color. The oil used in this step is filtered and refreshed continuously using an inline oil management system that maintains optimal frying conditions and ensures that the final product is never tainted by burnt residues or off flavors. The partially cooked chicken is then lifted out of the fryer via a conveyor system and deposited onto a draining belt that uses both gravity and air jets to remove excess oil. Now, it's time to transition to the flash freezing process. This is where partially cooked chicken is rapidly frozen to lock in all the flavors, textures, and moisture absorbed during marination and breading. Each piece is conveyed into a spiral freezer or impingement freezer, both of which use sub-zero air blasts or liquid nitrogen vapor to drop the temperature of the chicken from over 60 degrees Celsius to below minus 18 degrees in under 10 minutes. Rapid freezing is crucial to prevent the formation of large ice crystals, which can damage the cellular structure of the meat and result in dryness or texture loss after final cooking. During this process, each piece is also individually quick frozen, which prevents clumping and allows for precise portioning when packaging. The next step in the factory process is the automated packaging of the individually quick frozen, par-fried chicken pieces, a phase that combines high-speed precision machinery with meticulous control over product integrity. Once the chicken emerges from the spiral or impingement freezer, each piece is conveyed to a sophisticated vision inspection system that performs a final quality assurance check. High-resolution cameras and laser scanners examine each piece for uniform breading coverage, appropriate size, and the absence of any structural defects like broken bones or irregular shapes. Pieces that fail this inspection are removed from the line using targeted air jets and routed for rework or disposal, depending on factory protocol. Once the pieces pass inspection, they are conveyed into a portioning station where intelligent weighing and sorting systems group them into standardized sets that align with KFC's iconic bucket meal configurations. These could be 8-piece, 12-piece, or 16-piece configurations, depending on the regional product lineup. Multi-head weighing machines calculate the total weight and count of each portion, ensuring that every pack not only meets visual and compositional standards, but also falls within a narrowly defined weight range for inventory accuracy and consistent customer experience. These grouping systems operate at incredibly high speeds, hundreds of portions per minute, with tolerances as tight as +1 gram. Each portion of chicken pieces is then dropped into a form-fill-seal machine or into pre-formed plastic pouches, depending on the final packaging format. The form-fill-seal machines shape a plastic film into a bag, load it with chicken, flush it with a nitrogen-rich gas to minimize oxygen, and heat seal it in a continuous, uninterrupted process. Modified atmosphere packaging is used here to extend shelf life while preventing freezer burn or flavor degradation. The gas blend, often a mix of nitrogen and carbon dioxide, inhibits microbial growth and oxidation without adding any chemicals or preservatives. After sealing, the packages are labeled with all necessary tracking and compliance information. High-speed thermal transfer printers apply labels that contain lot numbers, plant codes, production timestamps, and freeze dates. These labels also include data matrix barcodes or QR codes used for traceability, allowing KFC's central quality control teams to trace every package back to its exact farm, batch, and processing line in the event of a recall or audit. Automated verification systems scan each label for accuracy and readability. Any incorrectly labeled packages are automatically rejected from the line and placed in a designated review bin for manual inspection. Now it's time to move on to case packing, where multiple individually sealed packs of chicken are grouped into corrugated cardboard boxes, each built to withstand long-distance cold chain transportation. Robotic arms equipped with vacuum suction grippers pick and place the sealed bags into the boxes with extreme precision, ensuring that space is maximized while maintaining the integrity of the chicken. Each case typically holds a specific number of meals or bucket configurations and is marked with a unique identifier. Once filled, the boxes are sealed using automated taping machines and pass through weight verification stations to ensure each box matches the expected load. Once packed, these boxes are stacked onto pallets using robotic palletizers. These robots follow pre-programmed stacking patterns that balance weight and maximize vertical space without compromising stability. Slip sheets and corner boards are often inserted between layers to protect the boxes during transit. Each completed pallet is then shrink-wrapped using a rotary arm or turntable stretch wrapper, which encases the entire stack in several layers of industrial plastic film to secure the load for transportation. A final barcode label is applied to each pallet, integrating it into the warehouse management system, which tracks every movement of inventory from production to dispatch. Next comes the crucial cold storage phase. The finished pallets are transferred via automated guided vehicles or high-speed conveyor systems into a massive cold storage facility, maintained at a consistent temperature of -18 degrees Celsius or lower. These storage facilities are designed with energy efficiency and inventory management in mind, often featuring high bay racking systems and vertical lift modules that allow for dense, organized storage. Temperature and humidity are monitored continuously by sensors linked to a centralized control room, where technicians receive alerts if any deviations occur. These warehouses are often equipped with backup generators and emergency protocols to ensure uninterrupted refrigeration in the event of power failures. After sufficient time in cold storage, which may range from a few days to several weeks depending on demand, the frozen chicken pallets are scheduled for distribution. The dispatch process begins with a pick and pack phase, where orders from various KFC regional hubs or franchise warehouses are collated. Advanced logistics software optimizes which pallets to pull based on freshness, production date, and delivery location. Selected pallets are loaded onto refrigerated trailers that maintain a controlled environment throughout the entire journey. These trucks use insulated walls and powerful refrigeration units that can be monitored remotely to ensure temperature compliance from factory to franchise. As these trucks transport the frozen chicken to regional KFC distribution centers or directly to individual restaurants, the cold chain is never broken. The receiving locations are equipped with cold storage facilities of their own, ensuring the chicken remains at safe temperatures until it's needed. At this stage, each restaurant receives a specific allocation based on forecasted customer demand, which is calculated using advanced demand planning software linked to point-of-sale data and regional market trends. The chicken remains sealed until it's ready to be used in the restaurant's kitchen, where the final stages of cooking take place. But now it's time to dive into the heart of the KFC restaurant kitchen, where the transformation from pre-cooked frozen chicken into the hot, crispy, golden brown pieces we all recognize occurs. After thawing in temperature-controlled refrigeration units for a specific number of hours, typically overnight, the chicken is brought to the breading station. Though the chicken was par-fried and breaded at the factory, a second layer of fresh breading is applied in-store to create the distinctive double crunch texture KFC is famous for. This is where the Colonel's proprietary 11 herbs and spices come into play. Each restaurant receives sealed tubs of this secret seasoning blend, pre-measured and tamper-proof. The thawed chicken pieces are first dipped into a cold, seasoned egg wash or a specialized batter mix, depending on the region. Then, they are placed into large breading bins containing the flour and spice mixture. Trained team members follow a specific press and fold technique, which involves pressing the flour onto the surface of the chicken and folding it multiple times to ensure full adhesion and the formation of the characteristic craggy, crispy coating. Each piece is then gently shaken to remove excess breading and laid out on wire racks to rest before frying. This resting period is short but essential. It allows the coating to set and adhere to the surface of the meat, reducing slippage during frying. Next, the chicken is placed into large open fryers filled with high-stability frying oil, often a soybean or canola blend, optimized for high temperatures and neutral taste. The fryers are preheated to exact temperatures, typically around 170 to 180 degrees Celsius, and the chicken is cooked under pressure for a controlled duration. KFC's use of pressure fryers is a distinctive element of its cooking process. The pressure cooking not only reduces cooking time, but also seals in moisture, ensuring the chicken remains juicy while achieving a perfectly crispy exterior. Sensors inside the fryer monitor oil temperature, pressure levels, and cooking duration down to the second. Once the timer signals completion, the fryer basket lifts automatically and the cooked chicken is removed using heat-safe tools to ensure safety and hygiene. After frying, the chicken is transferred to heated holding cabinets that maintain a precise internal temperature, typically around 60 to 65 degrees Celsius, for a limited time, usually no longer than 90 minutes, to ensure optimal freshness and food safety. These cabinets are fitted with internal timers and alert systems to prompt kitchen staff when a batch is nearing the end of its holding time. Any product not sold within this window is discarded according to food safety protocols to maintain KFC standards. Now that the chicken is hot, crisp, and ready, it's portioned into the familiar red and white striped buckets. Each bucket is made from food-grade, grease-resistant cardboard, printed with high-resolution branding that remains vibrant, even under heat and oil exposure. The buckets are assembled on-site from flat-pack form using pop and lock mechanisms and lined with waxed paper liners. The kitchen crew follows strict guidelines when arranging the pieces inside each bucket, ensuring an appealing visual mix of drums, thighs, wings, and breasts. The buckets are then sealed with fitted plastic or cardboard lids to retain heat and are either handed to walk-in customers or packed into thermal delivery bags for transport. The final stretch of the production process involves a complex web of quality assurance protocols, food safety audits, sustainability initiatives, and continual technological improvements, all of which are critical to ensuring that every KFC fried chicken bucket, whether purchased in Tokyo, New York, or Johannesburg, meets the same high standard of taste, appearance, and food safety. These behind-the-scenes systems may not be visible to the end consumer, but they represent the foundation of KFC's global manufacturing and supply chain model. One of the most rigorous systems in place is the Hazard Analysis and Critical Control Points, or HACCP, framework. This is applied across all phases of the production lifecycle, from live animal handling at the poultry farms to final packaging at the restaurant level. Every critical control point is identified, monitored, and logged digitally. For example, in the chilling process, sensors verify that the internal temperature of chicken pieces drops to below 4 degrees Celsius within a very specific time frame. If any batch fails to meet that requirement, the system will automatically flag the anomaly, prevent further processing, and isolate the affected lot until a manual inspection is completed. These digital controls are complemented by human oversight. Trained quality control technicians regularly inspect samples at random, visually assessing breeding adhesion, meat color, texture, and aroma. At the plant level, sanitation is treated as a mission-critical activity. Every line, blade, and conveyor is cleaned on a strict schedule using a validated multi-step process that includes rinsing, application of food-grade alkaline and acidic detergents, hot water sanitizing, and ATP testing to detect any microbial residues. Cleaning in place systems are used in closed-loop systems like marinade blenders and oil filtration units, ensuring deep sanitation without the need for dismantling complex machinery. Swabs are taken from surfaces and air samples collected to detect airborne pathogens, all analyzed in on-site microbiological labs. If even a trace of Listeria, Salmonella, or E. coli is detected, entire zones of the plant are shut down and sanitized before production can resume. In parallel to these food safety systems, sensory panels and culinary scientists at centralized R&D hubs conduct organoleptic tests to ensure product consistency. These tests assess everything from the crunch of the breading to the juiciness of the meat and the aroma released when the bucket is first opened. Chicken from multiple plants is cooked and compared side by side in blind taste tests to identify deviations in flavor or texture. If a factory's output strays from the baseline profile, its formulations and techniques are reviewed. In some cases, regional adaptations are permitted. For instance, a slightly spicier breading formula in Southeast Asia, or a less salty blend in Scandinavian markets. But these must be approved through corporate sensory panels and extensive pilot runs. Now it's time to take a look at how traceability and supply chain visibility are achieved at scale. Every piece of chicken can be traced through a blockchain-based system that logs data from farm to fryer. RFID tags and barcode labels track each pallet, batch, and case throughout its journey. When a truck departs a cold storage warehouse, its GPS location is monitored in real time, and its refrigeration status is transmitted back to the operations center every 5 minutes. If a delivery truck's temperature rises above the acceptable range for more than 10 minutes, alerts are sent automatically, and corrective actions are triggered, either rerouting to a nearby cold facility or discarding the load, depending on the severity of the excursion. Once the product reaches the restaurant, the store-level staff become the final link in the quality chain. Every team member is trained not just in food preparation, but in safe handling and equipment calibration. They measure oil temperatures with infrared thermometers before every cooking cycle, check holding cabinet thermostats each hour, and perform timed inventory rotations to prevent expired stock from being used. Any discrepancies are flagged in a digital checklist that is reviewed daily by shift supervisors and weekly by regional managers. Corporate auditors also perform unannounced inspections using checklists derived from international food safety certifications such as ISO 22000 and BRC Global Standards. But up next is a growing area of emphasis for KFC's manufacturing process, sustainability. As environmental concerns increasingly shape consumer expectations and regulatory policy, KFC and its supply chain partners have invested heavily in reducing their environmental impact without compromising efficiency or food safety. For instance, many factories now operate on hybrid energy models that integrate solar or wind power into the grid supply. Heat exchangers capture and recycle waste heat from fryers and ovens to preheat water for cleaning cycles. Water treatment plants have been installed adjacent to major facilities to purify and reuse water from scalding tanks and chilling baths, thereby reducing freshwater consumption by up to 60%. Waste management is another cornerstone of sustainable operations. Offcuts, bones, and organ meats removed during the evisceration process are rendered into protein meal for use in animal feed or fertilizer. Oil used during the par frying phase is filtered multiple times and eventually recycled through third-party processes into biodiesel or industrial lubricants. Even the breading flour that falls off during coating is collected, sifted, and reused within the same batch cycle if it remains uncontaminated thanks to high-speed sifters and air classification systems. Packaging materials are continuously redesigned to reduce plastic use, and many regional markets have adopted compostable or recyclable buckets made from sugarcane fiber or recycled cardboard. Now let's touch on automation and the future of food manufacturing. KFC's supply chain continues to push the boundaries of factory automation. Smart robotics now handle everything from chicken loading and cutting to box folding and pallet stacking. Machine learning algorithms analyze yield patterns, worker performance, and maintenance schedules to optimize output while minimizing downtime. Vision systems are paired with artificial intelligence to assess product quality in real time, not just based on weight and shape, but also by identifying anomalies invisible to the human eye, such as microfractures or uneven breading density. One of the most promising developments is the integration of digital twins, virtual replicas of entire production lines that allow engineers to test modifications in real time before applying them in physical factories. If a new breeding formula is under development, it can be modeled digitally to predict how it will behave under tumbling, par frying, and freezing conditions. These simulations save weeks of trial and error testing and reduce waste. Some facilities even employ predictive maintenance systems powered by sensors embedded in critical equipment. These sensors monitor vibration, temperature, and pressure, allowing for preemptive repairs before machinery fails, ensuring smooth operations and uninterrupted chicken production. KFC has also begun exploring vertical integration of its logistics chain. In some regions, specially designed micro-factories are situated closer to major urban centers, reducing transit time and carbon emissions. These micro-factories handle final stage breading and par frying, enabling fresher product delivery and enhanced responsiveness to demand fluctuations. Combined with real-time sales analytics from thousands of KFC restaurants, these decentralized production nodes can respond dynamically, ramping up or down based on foot traffic, promotions, or seasonality.